Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Silence. Darkness above, darkness below. An infinite and formless quiet. There is no up or down, no yesterday or tomorrow. Only a void, pregnant with potential, waiting beyond time. In the beginning, there is nothing. And then, in a single, trembling instant, nothing becomes everything. A blinding newborn light erupts from that void, birthing space and time together. The stage of reality appears out of the darkness, not empty, but carrying all that will ever be. The universe ignites with a flash, and the great cosmic drama begins. From that first furious moment, space itself unfurls, expanding, stretching, uncoiling faster than the speed of any light that will later travel through it. What was smaller than an atom swells to cosmic size in the blink of an eye. There is no outside to this expansion. Space is not expanding into anything. Space is simply growing, creating new space between everything, carrying galaxies in its flow like leaves on a rushing stream. In those first moments, the universe is a hot, dense plasma, a searing ocean of energy where matter and light are one, where the very laws of physics quiver in the newborn heat. It is a time before atoms, before stars, before any structure. Space is tiny, and space is absolute. All that exists is compressed in a blazing fog of creation, everywhere at once. The young cosmos swells rapidly. In a tiny fraction of a second, it doubles again and again, faster and faster. We call this fleeting epoch inflation, when the fabric of space-time ballooned mind-bogglingly fast, smoothing out any wrinkles. It's as if the universe took a deep breath and blew itself up like a balloon. Tiny random quantum fluctuations, minuscule imperfections, mere whispers of nothingness, were magnified to cosmic proportions. Those infinitesimal quantum jitters, born in absolute darkness, became the seeds of everything to come. From the very beginning, the illusion of nothingness hides creative power. Even empty space had flickers of energy, and those flickers grew to shape galaxies. Emptiness is never truly empty. It foreshadows all the structure that will later emerge. As space expands and ages, though it is only seconds old, it cools. The primordial fireball stretches out, its heat is diluted. Matter condenses out of energy, as if the cooling universe is crystallizing. In the first fleeting second, quarks join to form protons and neutrons. Within minutes, the first atomic nuclei appear. Simple hydrogen and helium, the lightest elements, fused in the inferno of the young cosmos. The universe is still a glowing plasma, a brilliant fog of particles and light intertwined. From the outside, though there is no outside, it would shine white-hot like the core of a star. Time flows, seconds, minutes, tens of thousands of years. The cosmic fireball expands and dims from white-hot to red-hot to a warm glow. Space is now vast and cooling, filled with a hot nebula of charged particles. Light, which had been trapped, scattering in the dense plasma, now finds conditions gradually easing. 380,000 years after the beginning, a threshold is reached. The universe cools enough for electrons to settle into orbits around nuclei, forming the first atoms. And suddenly, the blinding fog of plasma clears. The universe becomes transparent. Light is free to travel onward, free to illuminate the darkness. The great cosmic fog lifts, and darkness, which had been drowned in light since the first moment, finally has room to exist again. In that moment, the first light of the universe bursts forth across space. A gentle glow permeates everything, the afterglow of the Big Bang. It is a fossil light, carrying the imprint of creation itself. Today, we still detect this primordial light as a faint whisper in the microwave spectrum, coming from all directions, the cosmic microwave background. It is a cold, faint echo of that once blazing fireball, stretched to longer wavelengths by billions of years of cosmic expansion. In its mottled, feeble glow are tiny temperature ripples, the fingerprints of those ancient quantum seeds that inflation scattered. In those ripples lie the blueprint for the cosmic web of galaxies yet to come. But after that first light shines forth, there is a long darkness. The cosmos expands into a dark age. No stars shine yet. The elemental hydrogen and helium gas, left over from the Big Bang, fills space like an invisible fog. Gravity is at work, slowly drawing the gas into denser patches, but to the mind's eye, the universe at this time is a black void, starless and still. Imagine drifting through a cosmos with no stars, no galaxies, only vast, cold clouds where atoms are beginning a slow dance under gravity's pull. In pockets of slightly higher density, the gas gathers, falling inward like dew condensing, growing hotter and denser at the center of those pockets. Eons pass in darkness, millions upon millions of years of cosmic night. Then, at last, there is light again. Gravity's patient work pays off. The first stars ignite. Deep in a collapsing cloud of gas, the pressure and heat soar until hydrogen atoms fuse into helium, and a newborn star's fire ignites. One by one at first, then in clusters, stars wink on, piercing the cosmic night. Imagine that moment. After ages of black silence, suddenly pinpricks of starlight appear like a scattering of gems on velvet. The universe's second dawn has arrived, the cosmic dawn. These first stars are giants, many dozens or hundreds of times more massive than our sun, burning their fuel furiously bright and hot. They live short, brilliant lives, pouring ultraviolet light into the once dark universe. Their glow begins to dissolve the primordial fog, breaking apart neutral hydrogen atoms around them. Space, which had gone dark and neutral, is once again filled with energetic radiation. The first stars live fast and die young. In a few million years, some of them exhaust their fuel and explode as titanic supernovae, enriching the surrounding gas with heavier elements forged in their cores. Their deaths trigger more starbirths nearby, and soon clusters of stars are gathering. Gravity, always the silent choreographer, draws stars into protogalaxies, small nascent galaxies merging and growing. Over hundreds of millions of years, these gather into the first galaxies, blazing with starlight and sometimes harboring newborn black holes in their centers. The universe is no longer a quiet, empty void. It is alive with light and drama. These early galaxies are chaotic and strange by our standards. Collisions and mergers are frequent, their shapes turbulent, but from their collisions, larger structures begin to emerge. The universe's once diffuse matter has now knit itself into stars, star clusters, and galaxies. The stage of space that was set at the Big Bang is now populated with a rich cast, brilliant blue-white massive stars, glowing red embers of dying giants, swirling nebulae of gas and dust, and nascent star clusters bound by gravity. Yet space itself remains the seemingly empty backdrop for all this action. We gaze between stars and see blackness. It is tempting to think of that black vacuum as nothing, mere emptiness between the things in the universe. But space is not a passive void. It is the fabric on which this whole cosmic tapestry is woven, and it has its own character and geometry. The shape of space can be bent, the flow of time can be altered. Space can carry ripples. We call them gravitational waves, when massive objects like black holes collide, and space can even tear or fold in extreme scenarios. In our everyday experience, space seems rigid and flat, Euclid's grid extending uncurved in all directions. But nature's true geometry is subtler. Decades ago, Brilliant minds on Earth realize that space and time are interwoven into a four-dimensional fabric called space-time, and mass and energy can curve this fabric. Gravity, as we know it, is not a mysterious force acting at a distance as Isaac Newton once thought. It is the shape of space-time itself, telling objects how to move. Matter, in turn, tells space-time how to curve. Picture space as a flexible rubber sheet. Place a heavy object like a star on that sheet, and it sags, creating a well. Now a smaller object, like a planet, moving nearby will roll toward the star, not because of an invisible force pulling it, but because of the slope in the rubber sheet. In reality, the planet is simply following the straightest possible path in curved space, a path called a geodesic, which appears to us as an orbit. As one physicist poetically put it, matter tells space how to curve, curved space tells matter how to move. If there were no space to bend, there would be no gravity as we know it. Space is an active participant in the cosmic dance, shaping the trajectories of planets, stars, and light itself. Indeed, light, which we usually think of traveling in straight lines, can be made to bend by gravity. When starlight passes near a massive galaxy or a cluster of galaxies, the space-time curvature there acts like a lens, bending the light's path. Distant galaxies behind get their images distorted and magnified into arcs and rings. We on Earth have seen this, subtle smears and halos in our telescope images that are gravitational lenses, proof that space around the foreground mass is curved. Even the sun bends starlight passing near its limb, an effect once observed during a solar eclipse, confirming Einstein's bold predictions. Space, when stressed by mass, warps and flexes. Under the weight of extremely dense concentrations of mass, space can even collaborate with time to perform astonishing feats. It can slow time's passage relative to elsewhere, so clocks run a bit slower deep in a gravitational well than far away. We have measured this too. A clock on a mountain ticks just slightly faster than one at sea level, where Earth's gravity is a touch stronger. The difference is tiny, but real. To someone falling into a very strong gravitational field, say approaching a neutron star or black hole, time on their own clock seems normal, but an outside observer would see their movements slow down dramatically. In the extreme, as our traveler nears the point of no return of a black hole, to an outside eye they freeze in time, hanging there at the edge of darkness. Space and time are intertwined strands, and what one experiences as time another can partly experience as a curvature of space. The two cannot be separated. They are simply different directions in the same unified space-time fabric. Look around you right now. You might feel motionless, but you are hurtling through space. Our Earth is falling freely in the sun's curved space-time, orbiting at about 30 kilometers per second. That's 108,000 kilometers along its yearly path. Meanwhile, the sun itself is racing around the center of our Milky Way galaxy at roughly 200 kilometers, steered by the curvature of space caused by the galaxy's mass. Even as you sit, you are carried on a moving platform through a continually evolving geometry of space and time. We are all space travelers, embedded in orbital dances we mostly take for granted. Gravity's choreography is ceaseless. Planets swing around stars, stars orbit galactic centers, galaxies themselves twirl within clusters. Space is not a static stage at all, but a dynamic player. And nowhere is this more dramatically evident than in the most extreme arenas of gravity, black holes. A black hole is a region where space curves so steeply inward and gravity becomes so intense that nothing, not even light, can escape once it passes a certain boundary, aptly named the event horizon. To form such a monster, matter must be crushed into a very small volume. Nature accomplishes this in the death of massive stars. When a star far heavier than our sun exhausts its nuclear fuel, its core collapses under its own weight. If there's no force able to halt that collapse, the core continues imploding to an almost infinitely dense point. a singularity, and a black hole is born around it. What does a black hole look like? For a long time, it was pure speculation. By definition, a black hole emits no light of its own. It is literally a black spot in space. Yet we now have glimpsed one indirectly, by photographing the glowing orbiting gas around it and seeing the dark shadow in the middle where the hole's gravity prevents any light from escaping. There it is, a circular silhouette against a swirl of hot, bent light. This image, humanity's first direct portrait of a black hole, reveals a cosmic abyss, space falling inward like a waterfall at the speed of light, carrying everything with it. Approach a black hole, and gravity's pull grows without bound. Far away, you might orbit it safely, as one would orbit any mass of that size. Closer in, however, space curves ever more sharply toward the center. Cross an invisible spherical boundary, the event horizon, and escape becomes impossible. It is as though you've been caught in a cosmic current that flows only inward. No rocket, no beam of light can fight its way out once inside that horizon, because space itself is rushing inward too fast. You could fire the most powerful engines in existence, but you would still be drawn further in, like a swimmer caught in a swift waterfall that even light cannot swim against. From outside, we would never see you actually enter. We'd watch your image redden and dim, your time slow to a crawl, asymptotically approaching that boundary, but never quite crossing it. Meanwhile, you, falling in, experience none of this oddness directly. You drift past the event horizon with no sudden jolt. It's just empty space locally, and plunge towards whatever lies at the center. What lies at the center? Our equations break down, much as they did at the moment of the Big Bang. We predict a singularity, a point of infinite density and zero volume, a tear in the fabric of space-time. It is a place where our understanding falters, where quantum effects and gravity meet in unknown ways. In a sense, the birth of the universe and the center of a black hole are kin. Both are singularities, edges of space and time that defy comprehension. If you fall into a black hole, you head toward this end of space and time, though end may not even be the right word. Before reaching that ultimate point, however, a physical object would undergo extremes. As you descend, the difference in gravity's pull between your nearer side and farther side grows enormous. For a feet-first fall, your feet feel a stronger tug than your head. This tidal force becomes so strong that it stretches you grotesquely, a fate whimsically known as spaghettification. Any object, an astronaut, a spacecraft, a planet, would be pulled into a long, thin strand as it approaches the singularity. First, your body would be pulled apart into pieces, then those pieces into molecules, atoms, and subatomic particles. It's a one-way journey of disassembly. Space funnels everything inward relentlessly, compressing all fallen mass energy into that central point. Outside the black hole, we observe its presence by its gravitational influence. Stars orbit an invisible mass. Gas swirls into a glowing accretion disk around it, emitting X-rays as it is heated to millions of degrees. Sometimes, paradoxically, black holes trigger jets, as some infalling matter gets redirected along magnetic poles and blasted outward as high-speed particles, announcing the black hole's feast to the universe. But nothing that crosses the horizon returns. The black hole grows quietly with each meal, its horizon expanding like a gaping maw. Black holes can be small, a few times the sun's mass, or monstrous, millions or billions of solar masses in galactic centers. Our own Milky Way harbors a calm, supermassive black hole at its core, around which stars whirl in tight loops, like planets on fast forward. In distant galaxies, some supermassive black holes actively devour matter and blaze as quasars, outshining their entire galaxy, as infalling gas releases tremendous energy. Yet even these brilliant beacons are powered by what disappears forever from our universe into the hole's depth. If we consider the journey of a beam of light from the moment of the Big Bang's afterglow to now, we see how space shapes destiny. Light released at recombination, the clearing of the primordial fog, has been traveling for nearly 13.8 billion years and only now reaches our telescopes as the cosmic microwave background. Some light emitted by a star, formed soon after that time, traveled nearly the entire age of the universe to arrive here. We have captured such ancient photons. The Hubble Space Telescope, gazing into what seemed like an empty patch of sky for days, revealed the Hubble Ultra Deep Field, an image speckled with nearly 10,000 galaxies, some so distant their light set out when the universe was a mere 5% of its current age. Every tiny smudge in that image is a galaxy, each galaxy containing billions of stars. The emptiness wasn't empty at all. It was full of galaxies too faint for earlier eyes to see. Space, even in a dark, supposedly blank patch, was teeming with the light of distant worlds. In this way, light is the great messenger, carrying stories across time and space. When we look out into the universe, we are also looking back in time. The finite speed of light, about 300,000 kilometers per second, means that even nearby objects are seen as they were a little earlier. The sun we see is an 8-minute-old sun. It takes light 8 minutes to reach us. The nearest star system, Alpha Centauri, we observe as it was over 4 years ago. The Andromeda Galaxy, faintly visible in the night sky, is 2.5 million light-years away. We see it as it was when early human ancestors were just learning to walk upright. As we peer deeper, the look-back time increases. Telescopes are time machines in this sense. Point a powerful telescope to capture a dim red smudge that turns out to be a galaxy whose light took 12 billion years to arrive. You're seeing a fossil image of that galaxy as it was when the cosmos was young. We have, with our modern eyes, seen galaxies only a few 100 million years after the Big Bang. Toddler galaxies flickering into existence. We have even heard the ripples of cataclysmic events far across space, merging black holes and neutron stars billions of light-years away, their collisions shaking space-time itself and sending gravitational waves that we detected here, tiny vibrations in our instruments. These too are messengers, different from light, telling us that space can ring like a drum when titans collide. Where does the observable universe end? As we scan further and further, we hit a horizon, not a physical edge, but a limit beyond which light hasn't had time to reach us in the 13.8 billion years since the Big Bang. We might imagine a sphere around us, about 46 billion light-years in radius today, which encompasses all we can, in principle, observe. Beyond that cosmic horizon, there may well be more universe, perhaps infinitely more. But it lies forever beyond our sight, because light, or any information, from those regions has not, and perhaps will never reach us. In a way, this horizon is like the event horizon of a black hole, but in reverse. It's a horizon, not because space is dragging things in, but because space and time began a finite interval ago for us, and distant regions are being carried away faster than light by the expansion. The most distant light we can see is the cosmic microwave background itself, a sort of luminous wall of fog marking 380,000 years after the Big Bang. We cannot see earlier than that with light, because earlier, the universe was opaque. Thus, the observable universe has a shoreline in time, a point beyond which our light boat cannot sail. As the universe ages, this horizon shifts outward. Light from slightly more distant regions will trickle in, but simultaneously, the expansion of space continues to carry distant galaxies away. We live in an expanding universe, a discovery made not even a century ago. In the 1920s, astronomers peered at fuzzy spiral nebulae and discovered they were galaxies outside our own. Soon after, Edwin Hubble found that these galaxies are, almost all, receding from us, with their light stretched to redder wavelengths. The more distant the galaxy, the faster it appears to flee. The straightforward interpretation: space itself is stretching, and with it, the distances between galaxies increase over time. Galaxies are not moving through space away from us, so much as space between us is swelling, carrying them apart. To visualize, imagine raisins in a rising loaf of bread. As the dough expands, each raisin sees its neighbors receding. There is no central raisin. Every raisin sees the same effect. Similarly, from any galaxy's perspective, space expands and other galaxies, beyond its local gravitational group, move away. This expansion was initially thought to be slowing down due to gravity, like an explosion gradually decelerating. Indeed, for much of cosmic history, the mutual gravity of matter did slow the expansion. But to great surprise, around 1998, we found that in the last few billion years, the expansion has begun to speed up again. The universe is not just expanding, it is accelerating in its expansion, like a car that, after coasting uphill and slowing, suddenly hits the gas and surges forward. The cause of this cosmic acceleration? We give it a name: dark energy. But truthfully, the name is a placeholder for an unknown phenomenon. Dark energy seems to be an intrinsic property of space itself, a sort of energy of the vacuum that, rather than diluting as space expands, remains constant or even grows, thereby driving space to expand faster. It acts like a repulsive gravity on large scales. About 5 billion years ago, dark energy's effect became dominant over the attractive gravity of matter, and the expansion reversed its slowdown and began accelerating. Today, dark energy constitutes roughly 68% of the total energy content of the universe, with invisible dark matter about 27% and normal matter only about 5%. Space, it turns out, is filled with this mysterious pressure that shapes the fate of the cosmos. What does an accelerating universe mean for the future? It paints a picture of an ever more lonely cosmos. Distant galaxies will recede faster and faster. In 100 billion years, observers in our Milky Way, or its merged descendant, might see no other galaxies at all. They will have slipped beyond the horizon, their light stretched into oblivion by the expansion. The sky would be largely empty, except for the stars of our own galaxy. Over trillions of years, star formation will cease as the raw gas is used up or locked in remnants. Existing stars will age and die, leaving behind white dwarfs, neutron stars, and black holes. Those black holes, over unimaginable timescales, will slowly evaporate via Hawking radiation, turning their mass into faint photons and particles until they too wink out. The universe will enter a deep freeze, cold, dark, and dilute. Matter as we know it will be dispersed. Only thin gas and wandering subatomic particles will remain, nearly motionless in the expanding void. This is the projected heat death, or big freeze, where the temperature everywhere approaches absolute zero and time stretches on without much change. It is a somber, profoundly quiet end, not with a bang, but with a long, drawn-out whisper. Of course, this assumes dark energy remains constant. If instead it were to grow stronger over time, an option allowed by some theories, the acceleration could become so violent that galaxies, stars, planets, and eventually atoms themselves are torn apart in a hypothetical Big Rip. Alternatively, if dark energy decays or reverses sign, the expansion could slow and stop, perhaps even reversing into a big crunch where the universe recollapses, maybe to bounce and begin anew. But present data hint at the endless expansion scenario. The eternity of space looms, seemingly, as an ever colder, ever emptier expanse. Yet all of these distant futures and far pasts are extrapolated from what we know now, and what we know now is constantly expanding as well. We stand on a small planet roughly 4.5 billion years into the life of a rather ordinary star. In a typical galaxy, among billions, and only a tiny sliver of the cosmic timeline includes our presence. As we reflect on the cosmic past and future, we realize how brief and precious the living present is, the era in which stars shine, galaxies thrive, and life can flourish. So far, we have looked outward at the immensity of space. But to truly understand space, one must also look inward, to the tiny scales where quantum reality dominates. If we zoom in far enough, does space continue smoothly forever, or is it grainy, composed of fundamental units? Our best understanding of physics suggests that on the scale of the Planck length, about 1.6 per 10 tons 35 meters, mind-bogglingly small, our familiar notions of distance and even direction might lose meaning. Space and time may become quantized, divided into tiny indivisible units like pixels of reality. At such scales, space-time may roil in a quantum foam, constantly creating and destroying microscopic black holes and wormholes in a frenzy of uncertainty. No one has seen this foam directly. It's far beyond any current experiment's reach, but hints emerge indirectly. The vacuum of space, we know, is not completely empty. Quantum fluctuations continually spawn virtual particle-antiparticle pairs, which flit into existence and then annihilate, all within the uncertainty limits of quantum mechanics. These ephemeral entities have measurable effects. They cause slight shifts in atomic energy levels. They contribute to forces like the Casimir effect, and in the early universe, they seeded the galaxies. In a sense, space at small scales is like a seething cauldron, not a tranquil void. Even nothingness is busy. Our mathematics suggests that space and time may become completely blurred at the Planck scale. If one could shrink down to that scale, geometry itself might lose the smooth character we take for granted. Directions and dimensions might tangle. Cause and effect might become fuzzy. Is there an atoms of space-time? Tiny discrete building blocks? We don't yet know the answer. We seek a theory of quantum gravity to unite general relativity, which rules the large-scale structure of space-time, and quantum mechanics, which rules the microscopic world. Various ideas, superstrings vibrating in extraspatial dimensions, loops of quantum space-time, brains, and bulk, have been proposed. They paint exotic pictures. Perhaps our 3D space is embedded in a higher dimensional reality. Perhaps what we see as particles are actually vibrations of tiny strings in a multidimensional space. It's speculative, but tantalizing. One implication of some quantum gravity ideas is the possible existence of wormholes, shortcuts through space-time. Wormholes are often imagined as tunnels connecting two distant regions of space, and potentially time, through a higher dimensional fold. If space can curve and bend, maybe it can bend so much that 2 points touch, creating a throat that links them. In principle, general relativity's equations allow such solutions. The Einstein-Rosen bridge is one example, essentially a black hole mathematically connected to a white hole elsewhere. But wormholes, if they exist at all, come with huge caveats. They appear to require negative energy, exotic matter that has less than nothing in a sense, to stabilize and keep them open. Otherwise, they pinch off instantly. So far, we have no evidence nature produces traversable wormholes. Still, they capture our imagination. A traveler stepping through a shimmering portal and emerging light years away, or in another universe entirely, is a staple of science fiction, a modern echo of ancient folktales of magical doorways. Whether traversable wormholes exist in reality or not, they serve to remind us how flexible space and time might be under extreme conditions. The universe is under no obligation to maintain common sense at all scales or all realms. Under the extreme strain of a black hole's singularity or the entire universe's birth, space-time could do things we never see in ordinary life. Tie itself in knots, connect distant locales, or spawn new regions out of seemingly nothing. For now, these possibilities remain theoretical. But consider how far our understanding of space has come. To the ancients, space was the domain of gods and myths, the vault of heaven, the realm of ether, an unreachable firmament. Philosophers debated whether a void could exist. Nature abhors a vacuum, it was said. For millennia, space was just the gap between Earth and the celestial spheres, not something with its own identity. Then came the scientific revolution. Copernicus, Galileo, Newton. The Earth moved through space. Space became an infinite stage in which stars were other suns. Newton pictured space as absolute, an infinite, unchanging grid, and time as absolute too, ticking everywhere uniformly. Over 2 centuries later, Einstein shattered that comfort. There is no separate space and time, only space-time, and it is not absolute, but relative to the observer, pliable and curved. Space could stretch, contract, twist, as it does around a spinning object, dragging inertial frames. Suddenly, the stage could participate in the play. The interdependence of space and time is profound. Travel fast through space, and you experience less passage through time. Moving clocks run slow. This has been confirmed with particle accelerators and precise atomic clocks on fast jets. Spend 6 months on the International Space Station traveling at 28,000 km/s, and you'll come back a few milliseconds younger than identical twin on Earth, the so-called twin paradox in relativity, resolved by understanding the different reference frames. Space and time exchange in equations depending on motion. They are 2 faces of one reality. One cannot bend space without affecting time and vice versa. We have built our GPS satellites to account for both special relativistic time dilation, because they move fast, and general relativistic time dilation, because they are higher in Earth's gravitational field. Without those corrections, your phone's location services would drift off by kilometers. Thus, even in daily technology, the unity of space-time is at work. Our minds, evolved for the mid-world of moderate scales, struggle to truly picture warped space-time or quantum foam. But we can feel a sense of it through metaphors. Perhaps imagine a vast, flexible fabric with ripples and folds. That's space-time. On it, tiny flickers everywhere. Those are quantum fluctuations. Now and then, a massive weight falls on the fabric, making a deep well. That's a star's gravity, deeper for a black hole. If the weight is heavy enough, it punches through, a black hole connecting who knows where. Meanwhile, the entire fabric is stretching, slowly in some places, faster in others, carrying along everything sewn into it. If you pluck the fabric, a big merger, waves spread out, gravitational waves. It's an imperfect analogy, but gives a flavor. The reality surpasses imagination. Space contains all of us, yet transcends our intuitive grasp. We ask, is space infinite? It might be. Beyond our horizon, it could go on forever, or it might eventually wrap around like the surface of a sphere in higher dimension. Current observations hint that space is extremely close to flat and likely infinite, but we cannot be sure. We ask, is our universe the only one? Perhaps not. Some theories of cosmic inflation suggest bubble universes, each with their own space and time, disconnected from ours. If true, then what we call space might be just one bubble in a frothy multiverse sea, a local space-time encapsulated by something larger. Yet these other bubbles would be forever beyond our reach. So this remains speculation. Let's return to the tangible, to ourselves in space. Humanity has always been intimately connected to the sky. For tens of thousands of years, our ancestors looked up with wonder and told stories about the stars. The Milky Way band was a river of souls, or a spine of night, or spilled milk of a goddess. The darkness was feared, but also revered. In a way, we were aware of space emotionally and mythologically long before scientifically. We felt small under the dome of stars. We felt the infinite above press down on the finite below. Now, in the modern age, we have ventured into space physically. We have sent our machines to other planets and even beyond the solar system. We have, for brief moments, placed human footprints on the moon, another world, and brought back photographs that forever changed our perspective. One of the most iconic, Earthrise, captured by Apollo 8 astronauts as they orbited the moon. In that image, a barren lunar horizon arcs across the frame. Above it hangs the delicate blue marble of Earth, half lit against the black void. Seeing our world from afar, a fragile oasis in the vast darkness, was a profound moment in human consciousness. It was as if life's gaze had finally turned back upon itself and saw its home in context. A tiny, beautiful, lonely planet, suspended in endless night. Astronauts often report a powerful overview effect, a cognitive shift, when viewing Earth from space. They describe a deep sense of the unity of our species and the fragility of the biosphere. National boundaries vanish, petty conflicts seem absurd. There is just one world, shimmering blue with oceans and white with clouds, sitting in the velvet black of space. The thinnest wisp of atmosphere is all that separates life from lethal vacuum. Beautiful and fragile are words that come up again and again. Looking outward to the stars and seeing a vast emptiness, then looking back to Earth and seeing all of life in one tiny globe, must stir an existential awe unlike any other. It is humbling and illuminating. In space, our bodies and minds face new challenges. Those who have traveled to orbit find that their sense of up and down vanishes. In microgravity, astronauts must relearn how to move. At first, many feel a disorienting nausea as the inner ear's cues conflict with what the eyes see. Space adaptation syndrome, essentially motion sickness in freefall. The fluids in the body shift upward without gravity pulling them down. Faces become puffy, legs thin out, bird legs. Over time, bones and muscles, no longer bearing weight, begin to weaken. Astronauts lose bone mass at a rate of about 1% per month, despite exercise. Their muscles atrophy as well. Their hearts slightly shrink because pumping blood doesn't take as much effort. They must work out vigorously every day to mitigate these losses, using resistive devices and cycle ergometers. Otherwise, returning to Earth's gravity would be difficult. They might faint or struggle to walk after long missions. Despite all precautions, long stays in space do alter the body. Some experience degraded vision due to fluid pressure on the eyes. Cuts and wounds heal differently. Sleep can be disrupted by the lack of normal day-night cues. There is also radiation. Beyond Earth's protective magnetic field, cosmic rays and solar particles zip through spacecraft and human flesh. Over months, this exposure raises cancer risks and can cause subtle cellular damage. On a journey to Mars, astronauts would accumulate significant radiation dose, like getting many CT scans spread out over time. Shielding and careful timing to avoid solar storms are critical, but a degree of risk remains. Then there's the psychological dimension. Living in the confined, unchanging environment of a spaceship or space station for months, far from Earth, can strain the mind. Isolation, monotony, and the knowledge that home is hundreds of kilometers below or millions of kilometers away for future Mars explorers is a heavy burden. Astronaut crews are carefully selected for emotional stability and teamwork. They follow structured schedules to keep busy and maintain a sense of normalcy. But even the best can feel longing when they look out a window and see their home planet as a distant ball. One can only imagine the mixture of feelings, awe at the view, certainly, but perhaps also an acute loneliness or vulnerability. Earth, with all its familiar comforts and all of humanity, is out of reach except by radio. On the flip side, many astronauts report that while physically challenging, living in microgravity is also exhilarating. They speak of the pure joy of floating, of pushing off one wall and gliding effortlessly to the other side of a module. They develop a new spatial intuition. Down can be wherever you decide it is. They hang their sleeping bags on a wall or ceiling and drift off to sleep weightless, Some say it's the best sleep, like being cradled softly with no pressure points. Everyday tasks become novel. You must sip liquids from sealed bags. Since pouring a drink is impossible, it would break into floating blobs. And you must carefully corral every tool or spoon you use. If you let go, it might drift away and hide in some nook. There's a bit of humor and wonder in such scenes. An astronaut chasing a free-floating globule of coffee, slurping it like a lazy flying insect, or a stray pencil found bobbing behind a ventilator days after it escaped. Living in space is part high-tech endeavor, part childlike play in a gravity-free playground. All the while, just beyond the thin walls of the station or spacecraft is the void, a vacuum colder than 150 degrees Celsius in shade, blazing hot in sun, permeated by silence. Step outside on a spacewalk, and you are one tiny figure clinging to a metal island, with infinite night in every direction. If you turn your visor toward Earth, you see grandeur, continents and clouds rolling by in silence, 400 kilometers below, an immense sphere that fills half the sky. Turn away from Earth, and you face utter black, sprinkled with stars that don't twinkle, no atmosphere to disturb their light. They shine steady and innumerable, even against the blackness lit by the Milky Way's faint band. Some astronauts have described feeling a detached reverence on spacewalks, too absorbed in tasks to be emotional, until a pause allows them to drink in the view, and then, overwhelmed by the beauty and the sobering realization of being so far from home, protected only by a suit. It's a perspective few have experienced directly, but through their words and photographs, they've tried to share it with all of us. This leads us to consider consciousness and space in a broader sense. We, as thinking beings, always perceive ourselves as being somewhere. Our brains create a sense of space around us from sensory inputs. Even without sight, you feel oriented in a room by sound and touch. Our internal maps evolved in Earth's gravity, using down as a reference. In microgravity, astronauts must recalibrate their senses. Initially, many report feeling upside down half the time, or losing track of orientation. Yet the brain adapts. After a while, astronauts become ambidirectional, able to work regardless of rotation. The mind learns that in the absence of gravity, space is relative. Any way can be up. This adaptability of the brain shows how consciousness is tied to space, but not rigidly. We can adjust to new geometries. There's also a philosophical aspect. When humans left Earth, even just to orbit, it was the first time a living organism on our planet consciously detached itself from our ancestral home environment. That does something to the psyche. It enlarges the mental sphere in which we reside. Space travel expanded our consciousness outward, at least symbolically, to encompass more than Earth. We carry the aspirations and fears of our species into the void. As we floated above our world and looked back, we discovered not only knowledge, but a deeper understanding, an understanding that the pale blue dot below is singular and precious, and that the emptiness beyond is both hostile and beckoning. Some find in the enormity of space a profound loneliness. The universe appears indifferent, maybe devoid of other life, so far as we've found. The stars do not hear our cries. If we are indeed alone, the weight of cosmic solitude can be heavy. Others find in that same enormity a thrilling freedom, an endless frontier of possibilities and exploration. And many find meaning in the connection, that we are made of atoms forged in long-dead stars, that the iron in our blood and the calcium in our bones were birthed in stellar furnaces and supernovae. The universe is within us, quite literally, as much as we are within the universe. We are a way for the cosmos to know itself. Our consciousness gives the silent space a voice and awareness, if only in this tiny corner. From a certain perspective, space and consciousness are two sides of the same coin. Space is the external vastness we inhabit. Consciousness is the internal vastness that can contemplate it. Without minds to observe, would space have any meaning? Perhaps it would exist physically, but it would not be experienced. Through us, and perhaps other beings elsewhere, the universe gains the ability to reflect on its own existence. That thought can be humbling and elevating. We are small, yes, but not insignificant, because we carry the light of awareness. Throughout history, as we internalize the realities of space, our philosophies and religions had to adjust. Earth was no longer the universe's center. Humanity's place required a new narrative. We grew to understand that space is not up there. It's everywhere. The air between you and your screen right now is part of space. The gap between electrons and nucleus in an atom is space, and proportionally, a huge one. We ourselves are mostly empty space by volume. If an atom were blown up to the size of a stadium, its nucleus would be a grain in the center, and electrons like dust motes whirling near the stands. Everything else is empty. In that sense, we are made mostly of space. Solid matter is an illusion of scale. On the atomic level, there's vast nothingness with tiny, energetic particles dancing. The solidity you feel when you press your hand on a table is the electromagnetic fields of your atoms, repelling those of the table's atoms, never truly touching. You have never actually touched anything in the sense of your atoms contacting another's. There is always a tiny separation, filled with fields, with space. Thus, the space within is as important as the space without. We carry echoes of cosmic void in each of our atoms' architecture. We have talked about giant things and tiny things, about birth and death of worlds, about knowledge hard-won and mysteries remaining. Let us now zoom out again to a cosmic perspective and take stock. Here we are, small, curious, yearning, on a planet that orbits a star in a galaxy among billions, in a universe about 13.8 billion years old, and possibly infinite in extent. We have discovered that space is not empty, but filled with structure. Galaxies strewn like glitter, clusters and chains forming a cosmic web with great voids in between. Light crisscrossing the darkness, carrying memories of the past. Gravity sculpting the ballet of worlds. Dark matter lurking unseen, holding galaxies together. Dark energy pushing the fabric of space wider and wider. We have found that on the largest scales, space is remarkably uniform and flat. Yet on smaller scales, it is richly textured. We have found that space can bend around mass and even ripple when massive bodies move. We have found evidence that the universe had a beginning in time and has been evolving ever since, giving lie to the old idea of a static eternal cosmos. And we see that we are approaching some profound questions. Why does space have 3 large dimensions, and maybe hidden ones? What is the ultimate fate of space? Are there other universes, other spaces beyond ours? These questions border on metaphysics, but they also drive physics forward. Space is vast beyond imagination, yet intimately familiar. We move through space every moment of our lives. It is both an arena and an actor. It shelters us and can kill us. It separates us from other stars, but also connects us to them, since we share the same space. Perhaps the true nature of space is that it is relation. It is what exists between things and gives them their positions and sizes. Without space, no separations. Without time, no change. Together, space-time is the grand framework of existence. In the end, thinking about space always circles back to thinking about ourselves. We fill our maps with stars and galaxies, but inevitably mark an X labeled, "You are here." Contemplating the sprawling universe can make one feel small, yes. A single beat of a heart against 14 billion years. A single human against 100 billion galaxies. But consider, all those galaxies and all those years, and we can hold them in mind. Our minds, a product of the universe, can encompass the universe. That is a wondrous feedback loop. As we gaze out on a clear night, standing perhaps on a hill far from city lights, we see a sky that our ancestors recognized and yet did not. The Milky Way arches overhead, a river of countless stars. A smoky patch is Andromeda, our sister galaxy. Points of light are not gods or holes in a firmament, but distant suns, many with their own planets. We now know that the blackness between stars is not pure void, but filled with tenuous gas and dust, and further out, suffused with the faint afterglow of the Big Bang. We know that above us satellites are flying, and astronauts on the space station occasionally drifting across the sky as a fast-moving star-like dot. We might recognize planets wandering among constellations, Mars glowing red, Jupiter bright and kingly. With binoculars, we could see the Orion Nebula, a stellar nursery, or the glow of the Andromeda Galaxy. With a telescope, even more structure leaps out, spiral arms, clusters, comets' tails. We carry the collective knowledge that every one of those is a place in space, reachable at least in theory, governed by the same physics that governs our own world. The unity of physical law across space is another profound realization. A helium atom, on the edge of the observable universe, has the same spectral lines as one in our lab. Gravity operates the same in a galaxy a billion light-years away as here, though the relationships might be exotic there. This allows us to understand far-flung phenomena by studying local physics, a fortunate feature of reality. What of the philosophical meaning of space? To some, the vastness means freedom, an endless frontier that promises growth, expansion, adventure. To others, it means insignificance, a stage so enormous that we, the tiny players, seem to hardly matter. Space can evoke loneliness, as one imagines drifting eternally without finding another living soul. Or it can evoke unity, as when one sees Earth from space and realizes every human that ever lived did so together, on that one small globe. Space may feel eternal, making our lives seem fleeting, but it also casts life's brevity in sharp relief, perhaps encouraging us to cherish each moment more. Imagine for a moment a scene, perhaps in some future, or perhaps only in a dream. A person stands on the surface of Mars at dusk. Above, two small moons appear, Phobos and Deimos, racing across the sky. The sun, smaller and dimmer than on Earth, sinks below the rusty horizon, painting the thin sky salmon pink. As night falls, the stars come out in unbelievable clarity, no thick atmosphere to blur them. Our Milky Way glitters, and there, perhaps on the eastern horizon, a bright star slowly rises, with a faint bluish hue. It is Earth. Our explorer on Mars pauses in their work and gazes at that star. On that distant point of light is everything they cherish, all of humanity, oceans and forests, music and laughter, friends and family. An intense longing might well up, an emotional gravity pulling their heart across the void, but also a swell of pride or satisfaction. We came this far. Space allowed us to leave home, to see ourselves from new perspectives, to extend life's reach. In that moment, perhaps our Martian pioneer feels both utterly alone and deeply connected. The silence of the Martian night is profound, yet through the radio they hear colleagues, and in their mind, they hold the image of 8 billion souls back home, looking up perhaps at the same time, wondering about them. Every moment of human life has unfolded within space. We wake under a sky, we build walls and roofs to partition space for our comfort. We travel to work across town or across oceans, all movements in space. When a baby takes their first steps, when a loved one hugs you, when a dancer leaps, it's all spatial. Even when we dream, we conjure spaces in our mind's eye to move through. We cannot escape space. We are embedded in it as deeply as fish in the sea. And so space is not out there. It is here. The air around you, the room you sit in, the gap between the Earth and Moon, all of that is space. We already live in space. Earth is not separate from the cosmos, it is a part of it. Our planet is traveling through space on its yearly path, and we along with it. In a very real sense, space is home. It's just that, as the saying goes, we have to bring our own atmosphere. But once you realize Earth is an island in a vast ocean of space, and that ocean permeates every corner of existence, the notion of home expands. Home is the solar system that birthed our Earth, the sun that gives us energy, the protective magnetic bubble that shields us. Home is also the Milky Way galaxy that gave birth to the sun, and the universe that gave birth to the Milky Way. We emerged from the universe and remain a part of it, not apart from it. Thus, space is not foreign or hostile in the ultimate sense. It is simply nature on a grander scale. It can be dangerous, yes, but so can the depths of Earth's oceans or the peak of Everest. Yet we still explore and sometimes settle those places. Over time, we may extend our dwelling to multiple planets or space habitats, learning to create little Earth-like bubbles wherever we go. We will always need some of Earth's familiar comforts, gravity, water, air, ecological support, to truly thrive. But perhaps our ingenuity will let us transport a bit of Earth with us as we voyage farther. Standing at the twilight of one world and the dawn of another, we feel the eternity of space stretch out before us, full of mysteries, dangers, wonders. The stars above do not hand us their secrets. We earn them through effort and curiosity. And the reward is the cosmic perspective, a realization that the molecules in our bodies were forged in stellar cores and supernovae, that the heat keeping us warm originates in the nuclear furnace of an 8 light-minute distant star, that the very space enabling us to exist connects us to everything else. In this journey, from the silent darkness before the first dawn, through the fire of creation, the weaving of the cosmic web, the formation of stars and planets, the bending of space by gravity, the extremes of black holes, the expansion driven by dark energy, the quantum foam beneath reality's smooth surface, the dreams of shortcuts through wormholes, the courage of living in the void, to the vantage of consciousness reflecting on it all. In this journey, we come to a profound insight. Space is not empty. It is alive with story. It is the ever-present stage and actor where reality unfolds and evolves. It is the canvas on which time paints existence. As we conclude our exploration, imagine once more the deep silence of the cosmic night. But this time, it is not frightening or cold. It is serene, sublime, like the quiet of a vast cathedral, where the light of billions of stars are the candles. In that silence, you might sense something almost like a voice, not speaking in words, but in the language of awe and connection. It whispers that we are a part of this grand scheme, that the atoms in our bodies and the thoughts in our heads are woven from the fabric of the universe. We belong here as much as any galaxy or star. Looking up, you feel the weight of your body held by Earth's gravity, anchoring you to your home, yet your mind soars, unbound, into the stars. You are bridging the very gap of space with your awareness. In that moment, perhaps you understand that home was never just the ground underfoot or the walls around you. Home is existence itself, the totality of space and time of which we are an inextricable part. Space is not distant. Space is here. The universe is our address. And so, under the eternal light of billions of suns, on the edge of forever, we step forward. We carry with us the dreams of our ancestors, who once looked up in wonder, and the tools and knowledge gained by daring to ask questions. The void welcomes and challenges us in the same breath. We may sometimes feel tiny, but we have something the endless reaches of nebulae and clusters do not. We have eyes to see them, minds to know them, and hearts to be moved by them. In that way, we give the universe meaning, and it gives us meaning in return. Space is the everlasting backdrop and the intimate medium of our lives. It is dark, but filled with light, empty, but full of treasures, silent, yet it inspires symphonies within us. As we end our story, we find ourselves back in the quiet darkness of a starry night, not fearful, but filled with reverence. Above, the Milky Way's pale band is a reminder of our galactic home. One of those stars is the Sun. Around it orbits Earth, and on Earth, at this very moment, a person stands in the dark, looking up, feeling the gentle night breeze, and understands, finally, that they are not outside of the universe looking in, but an inside part of it looking out. In the grand, dynamic living stage of space, we have always been home. Between the stars, there is a darkness deeper than night. We call it space. It seems empty, a gaping void stretching in all directions, a vast nothing. Yet that nothing holds everything. It cradles the stars and planets, the light and the dust, the silence and the echoes of creation. Space is the gulf between things, the separation that defines each object and moment, but it is also the connective tissue of the cosmos, an invisible thread weaving all things together. Without it, no distance could lie between 2 points, nothing to measure, no here, no there. With it, the universe can spread out and become. Space is absence and presence at once, the emptiness that gives form to what is not empty, the vast inky canvas on which galaxies are painted. Look up on a clear night, far from city lights. You see countless stars sprinkled on a black dome. The darkness between them feels like a void, but consider that this darkness is not mere nothing. It is a stage, an arena, a medium. It carries the faint glow of distant galaxies, the whispers of ancient light. It holds the earth in its invisible embrace and extends beyond the farthest horizon our eyes will ever behold. In that darkness, every possibility exists. As an old proverb teaches, a cup is useful only because of the empty space inside. So too, the emptiness of space is what allows stars to shine, planets to orbit, and life to breathe. Space is the womb of the world and the ocean in which we float. We have always been its children, even when we huddle against the illusion of solidity on the ground beneath our feet. For millennia, humans have been both awed and unnerved by the void above. Before philosophy and science, early humans looked up and filled the darkness with stories of gods and heroes, of animals and spirits traced in the star patterns. These stories were our first attempt to make sense of the void, to tame its terror with imagination, and to express our awe. That human need for wonder has never left us. It merely found new forms. We still create stories of space, now with equations and telescopes, but also with dreams and art. Ancient philosophers pondered whether that void was truly nothing or filled with some invisible ether or celestial substance. To some, the night sky's darkness was sacred, the abode of gods or the shining realm of ancestors. To others, it was simply emptiness, terrifying in its boundless silence. We have peered up and wondered, what is the nature of that endless black? Is it mere emptiness between the stars? Or something deeper, a structure, a substance, an entity in its own right? As our understanding grew, we found that space is not an inert backdrop, but a dynamic, vital part of reality. It is not nothing at all. It has shape and structure, storms and whispers. It can bend and ripple. It erupted into existence and may one day fade. It connects the smallest atom in our bodies to the farthest galaxy in the universe. Space is the distance between us, yet it binds us to everything. It is the silence between notes in a grand cosmic symphony. Without the silence, the music could not be. In the same way, without the vast quiet of space, The brilliant fires of stars and the whirling patterns of galaxies could not exist or be perceived. Space holds time, matter, and even thought, an infinite stage where every story, including our own, unfolds. Already, we can sense that in exploring space, we are exploring ourselves as well, our origins, our essence. Think of the ground we've covered, space as a void and as a fabric. Its birth in the Big Bang, the quantum flickers in emptiness, the bending of starlight and the warping of time, the colossal structure of galaxies, the enigmas of dark matter and dark energy, the mysteries of black holes, the faint horizon of what we can see, the bravery of human explorers, and the tenderness of our consciousness nestled in a cosmic cradle. Each theme connected, forming a tapestry of understanding. Now, in that spirit, let us embark on this journey from the birth of the universe to the far future, from the smallest quantum flickers to the grandest clusters of galaxies. Let the story begin, as it always has, in darkness. But space was not always as we know it now. There was a time, if time is even the right word, when space itself was nowhere and nothing. In the beginning, there was not even emptiness, for there was no space to be empty, no distance, no outside or inside, no before or after. All that would become the universe was concentrated in an unimaginably small, hot point. In that primordial state, the seed of everything was contained in something infinitesimal, where the distinction between here and there meant nothing, because there did not yet exist. Then a flash, a furious expansion, an event we call the Big Bang. It was not an explosion in space, it was an explosion of space. Space itself unfurled from that first moment, swelling like a new blown bubble. In the first fractions of a second, the universe grew from smaller than an atom to larger than a galaxy. It was a blooming of space-time, a rush of creation so extreme our minds struggle to picture it. Time and space came into being together, intertwined from the start. In that instant of Genesis, energy roared forth, blazing light filled the young cosmos, and the very fabric of reality began to stretch. Try to imagine it. All of space compressed into a point and then suddenly expanding outward. There was no center in the usual sense. Every point in the nascent universe was the center, because the whole thing was expanding everywhere at once. The cosmos was incandescent, a churning plasma of particles and light. As space expanded, it cooled. In mere seconds, the hot broth of creation settled enough for the first protons and neutrons to form. Matter and antimatter were born in pairs, and almost all annihilated each other in flashes of gamma rays. But a tiny excess of matter, our future world, survived. In the next few minutes, those protons and neutrons fused into the first atomic nuclei. Hydrogen and helium, the lightest elements, formed in abundance as the fireball universe briefly became a nuclear furnace. Hundreds of thousands of years passed as the universe kept expanding and cooling. It remained blindingly bright, like the interior of a star, but that light was trapped in a dense fog of charged particles. Slowly, space grew vast and cool enough for electrons to settle into orbits around nuclei, forming the first atoms. Suddenly, the fog cleared. Light could travel freely across space for the first time, bursting outward as a great decoupling glow. That ancient light still washes over us today as a faint afterglow, a whisper from when the universe was newborn. Thus, space, once a pinpoint of fury, became an ever-expanding volume. Galaxies would coalesce billions of years later, but already the stage was set. Space had been born carrying time along with it. The distance between things began to grow, and with distance came the potential for structures, for motion, for cosmic evolution. The immense voids and stretches we now call space were initially tightly folded in that first moment. We are living in the aftermath of that expansion, Space is the legacy of the Big Bang, the arena inflated from that primordial flash. Every meter of empty space we traverse, every gap between star and star, was forged in that first event. In a sense, we are still inside the Big Bang, living in its cooling embers many eons later, as space continues to stretch around us. Now, as space grew and cooled, it might be tempting to think that truly empty space, pure nothingness, began to exist in patches where matter had yet to gather. But modern science reveals a profound paradox. Even the emptiest space is not truly empty. What we call a vacuum, devoid of atoms or light, is more like a restless ocean than a tranquil void. Imagine looking at a calm sea from afar. It appears flat and still, but up close you see incessant ripples and eddies. Similarly, what seems like pristine nothingness at the grand scale seethes with subtleties on the smallest scales. According to quantum theory, fields permeate all of space. Fields for electricity and magnetism, for gravity, for every kind of particle that can exist. These fields cannot be shut off. Even in a perfect vacuum, they retain a minimum energy, a jitter. Particles flicker into being from that energy and vanish almost immediately, like fleeting sparks in the dark. These aren't particles in the usual sense. They are virtual particles, born of uncertainty, living on borrowed time and energy, yet their effects are real. In the laboratory, if you place two metal plates extremely close together in a vacuum, the simmering vacuum energy between them changes and produces a subtle force pushing the plates together. The void exerts pressure. Nothingness has potency, so the void is full of potential. Empty space is more like a field of fields, all overlapping, invisible but present. Even when you remove every atom and every ray of light, space still retains this ground-level buzz of activity, a gentle quantum foam. This is sometimes called zero-point energy, the energy that remains when you take everything else away. It is staggeringly small in any tiny volume, yet because space is so vast, the collective effect of this vacuum energy might shape the cosmos. In fact, it could be related to the mysterious dark energy that is making the universe's expansion accelerate, an idea we will return to. In effect, the ancient notion of an all-pervading ether finds a new and unexpected echo. The fabric of space itself may be suffused with an exotic form of energy. Ponder that for a moment. The darkest, emptiest corner of intergalactic space, a million light-years from the nearest star, still isn't truly empty. It contains the gravitational field stretching from distant masses, the ever-present field that endows particles with mass, and the jitter of quantum fields spawning ephemeral pairs. Space is like a silent symphony, where, even in the pauses between notes, a faint vibration hums. Nothingness, it turns out, is a sort of something. Philosophers long ago suspected as much, proposing that emptiness might hold hidden qualities. Here, science and philosophy meet. The vacuum is a paradox, a no-thing that is also a sea of energy and possibility, the blank canvas that is never truly blank. This paradox of nothingness gives us a new reverence for space. When we speak of the void, we now know it has structure and behavior. Empty space can bend and flex. It can carry waves, not sound waves, but gravitational waves, ripples in space-time itself. It can even spawn new space. Since the Big Bang, space has been stretching and generating more of itself. The emptiness that nature supposedly abhors is in truth rich and creative. In the vacuum of space, particles appear and disappear incessantly, and with them come forces and consequences. It is as though the universe, even when seemingly doing nothing at all, still whispers beneath the silence. The void is alive with the potential for everything. After all, it was out of an initial nothingness that the cosmos itself blossomed. From empty space sprang the fullness of the world, and even today, emptiness continuously lends reality its shape. Space, as we have seen, is far from a passive void. One of its remarkable properties is its ability to bend, warp, and curve in the presence of mass and energy. Gravity, which we experience as the attraction between masses, is in truth an expression of curved space and time. Massive objects distort the fabric of space-time around them, much like a bowling ball placed on a trampoline stretches and curves the surface. If you roll a marble near that bowling ball, the marble will spiral inward, not because the ball reaches out and pulls it, but because of the dent in the surface. So it is with planets orbiting stars and stars orbiting galactic centers. They are following the curves of space carved by gravity. Picture the space around the sun. The sun's great mass dents space into a kind of bowl shape. Earth is like a smaller marble caught in that bowl, perpetually rolling around the slope. We don't fall in because, in a sense, we are already moving sideways fast enough to circle around. Space guides our planet's path. Every object with mass does this, though usually the warping is tiny. You, right now, are bending space around you, but the effect is unimaginably small. A planet or star makes a noticeable curve, and near something as massive as a neutron star or a black hole, space-time curves dramatically, steepening into a deep well. This idea that gravity is geometry revolutionized our understanding of the cosmos. It means that space is elastic, shapeable. It can be stretched, as in the expansion of the universe, and it can be curved by mass. Space and time are woven together, so when space bends, time does too. A clock deep in a gravitational well, say on the surface of a dense planet, will tick a bit more slowly than a clock far out in space, where space-time is less distorted. Even light, which has no mass, feels the influence of curved space. It travels in what we perceive as a bent path when it passes near a massive object. We have seen starlight curve around the sun during eclipses, and distant galaxies appear distorted into arcs by the gravity of intervening galaxy clusters acting as cosmic lenses. Space is not a rigid backdrop. It is a flexible, active player in the cosmic drama. When massive objects move suddenly, imagine two black holes spiraling together and merging. Space itself can ring like a drum. Waves ripple outward at the speed of light. These are gravitational waves, faint tremors in the fabric of space-time, spreading across the universe. They are extremely subtle. By the time they reach us, they stretch and squeeze distances by less than a fraction of an atom. Yet with delicate instruments, we have detected these ripples, listening as black holes billions of light years away collide. In those moments, space carries a form of music. Not sound, there is no air in space for sound, but a gravitational melody that we can hear with the right instruments. It is a reminder that even in silence, there can be vibration and song. So gravity is the shape of space and time. Everything with mass tells space how to curve. The shape of space tells matter how to move. This intertwined dance means that space is almost like a fabric, dynamic and alive. A heavy object makes an indentation. A moving heavy object can send ripples. On Earth, we are rarely aware of this truth because we live in the same curved space as our planet. Like ants on that curved trampoline, we don't directly see the dent from our perspective, but we feel it as the force that keeps our feet on the ground. When we launch a rocket, we are essentially giving it enough speed to climb out of the curved well of Earth's gravity. Once in the gentler slopes of space away from Earth, a spacecraft can coast, looping in the broader, shallower curve of the sun's gravity. In the vacuum of space, light races at the fastest speed possible, about 300,000 kilometers per second. Even so, the universe is so vast that this incredible speed has its limits. Light takes time to travel, and thus as we gaze out into space, we are also looking back in time. This is one of the most profound realizations in astronomy. Distance in space is literally distance in the past. When you look at the moon, you see it as it was about 1.25 seconds ago, because that's how long its reflected sunlight takes to reach your eyes. When you watch the sun dip below the horizon at sunset, the sun has actually already set 8 minutes earlier. Its last rays are just now arriving. Extend this further. The light from the nearest star system, Alpha Centauri, started on its journey over 4 years ago. The glow of the Andromeda galaxy, faintly visible on a dark, clear night as a hazy smudge, left that galaxy more than 2 million years in the past, when early humans were just beginning to walk upright on Earth. And the light from the most distant galaxies we can see started its journey billions of years ago, long before the Earth itself existed. Space is a time machine. The deeper we peer into space, the further back in time we see. In the darkness overhead is a kind of layered record of history. Nearby stars showing recent centuries of their past. Distant galaxies offering a view of epochs long gone. The most distant light of all, the cosmic microwave background, is the afterglow from the birth of the universe itself, now stretched and cooled to a faint whisper in microwaves. That light has been traveling for nearly the entire age of the universe, almost 14 billion years, only now reaching our telescopes. When we capture it, we are capturing a baby picture of the cosmos, a portrait of space when it was only 380,000 years old. This means that when we study the universe, we must reconstruct events like archaeologists. We cannot see the universe as it is in this exact moment everywhere, only as it was when the light left each region. In a real sense, the night sky is full of ghosts, the images of stars that may no longer exist, the echoes of supernovae that exploded eons before humans learned to make fire. Yet these ghosts are our guides. By reading the faint light, with its colors and patterns, we uncover the story of galaxies and stars. The redshift of a distant galaxy's light, stretched to longer wavelengths by the expansion of space during its journey, tells us how far that light has traveled, and thus how long ago it started out. Thus, we piece together the chronicle of the cosmos, seeing chapter by chapter of the past. Powerful telescopes today can see galaxies that formed when the universe was only a few 100 million years old, a small fraction of its current age. With each technological leap, from the first ground-based spyglasses to space observatories that see infrared glimmers of the earliest stars, we extend our vision and push deeper into time. Recently, a new generation of telescopes has begun to reveal galaxies taking shape just a couple of 100 million years after the Big Bang, challenging our models of early cosmic history and showing that the universe may have built structures faster than we thought. Surprises like these remind us that space still holds many secrets waiting to be discovered. Our cosmic story is continually refined with each new observation. It is often said that to look into space is to look into our origins. Because light needs time to travel, the farther out we observe, the closer to the Big Bang we approach in time. We are essentially observing the cosmic dawn, the first generation of stars igniting and the first galaxies assembling. We stand on our tiny world, collecting ancient photons that have crossed the gulf of space for eons, and from them, we learn what happened long before we came to be. There is a quiet poetry in this. The darkness of space is not just an absence of light, but a vault of ancient memories, waiting to be seen by those with eyes to see and minds to understand. In contemplating the vastness of space and the finiteness of light's speed, one begins to grasp the tremendous scales involved. The universe's stretches are almost beyond imagination. But one way to feel the magnitude of cosmic emptiness is to compare it to the emptiness we carry within ourselves, within the atoms that make up our bodies. Every atom is mostly space. If an atom were enlarged until its nucleus was the size of a marble, the atom's outer edge, where the electrons roam, would be nearly as large as a football field. The nucleus sits tiny and heavy at the center, and the electrons are like distant motes buzzing around the edges. The vast majority, over 99.9999% of the atom's volume, is empty space. That means the solidity we feel, this page, your hand, the ground, is an illusion created by electromagnetic forces in what is otherwise void. You, me, the rocks and trees. We are built of tiny solar systems of emptiness with infinitesimal specks at the core. The distance between those specks and their electron clouds, relative to their size, is enormous. Emptiness is woven into matter itself at the smallest scales. Now scale up. The Earth orbits the Sun at about 150 million kilometers away, a distance so great that light itself takes 8 minutes to cross it. Yet on the scale of the solar system, that is a modest gap. Our solar system is mostly empty space. If the Sun were a ball the size of a grapefruit, Earth would be a tiny pebble orbiting about 15 meters, 50 feet away. Jupiter would be another marble dozens of meters out. And beyond Neptune, the farthest major planet, lies a stretch of space so large and sparse that the mind reels. Vast cometary clouds, extending perhaps a quarter of the way to the nearest stars, containing only thin dust and ice fragments drifting in the dark. The nearest star beyond our Sun is so far that analogies barely do it justice. If the Sun were that grapefruit in your city, the closest star would be another grapefruit thousands of kilometers away, perhaps on another continent. In between would lie nothing but the darkness of interstellar space. Maybe a few stray molecules, the odd dust grain, but essentially vacuum. This gulf between stars is typical in our galaxy. Though the Milky Way is a city of hundreds of billions of stars, each star is light years from its neighbors. A light year is about 9.5 trillion kilometers, or nearly 6 trillion miles. Even a beam of light needs years to go from one star to the next. Our galaxy is about 100,000 light years across, a staggering expanse where, even at light speed, it would take 100 millennia to traverse from edge to edge. Between galaxies, the distances grow even more daunting. The Milky Way and the Andromeda Galaxy, our nearest large neighbor, are separated by about 2.5 million light-years of emptiness. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate a few meters away. Two enormous disc-shaped systems, each with hundreds of billions of stars, drifting slowly toward each other through a sea of darkness. And beyond our local group of galaxies, there are immense voids where, for tens of millions of light-years at a stretch, not a single galaxy shines. True cosmic abysses, nearly devoid of matter. The scale of separation in the cosmos is truly unimaginable. It humbles any human scale we know. Our minds evolve to comprehend the distance of a thrown spear or the walk to a neighboring village, not the gap to a neighboring galaxy. Yet here we are, straining our thoughts to encompass billions of light years. We invent metaphors, atoms like stadiums, stars like distant grains of sand, to bridge the gap between our everyday experience and these extremes. Even so, the reality remains staggering. Almost everything is space. The cosmos is a faint scattering of islands, stars, galaxies, in a vast ocean of nothingness. If you could compress all the matter of the universe together, eliminating the empty space, it would occupy a surprisingly small volume compared to the volume of space it currently fills. By volume, the universe is overwhelmingly void. This emptiness, however, is not a flaw or a waste. It is what allows room for structures to form without immediately colliding. It is what permits planets to orbit stars safely, stars to move in galaxies, galaxies to dance in clusters without constant destructive encounters. Space provides the breathing room for existence. The great gulfs between atoms prevent solid matter from collapsing in on itself. The light years between stars prevent gravitational chaos. The void between galaxies gives each galaxy the solitude to evolve its own magnificent form. The separations define the structures. The nothingness shapes the something. In this way, the distance between things is also the thread that connects them in the grand design of the cosmos. If we could pull our perspective even farther back, far beyond our galaxy, beyond our local cluster of galaxies, we would begin to discern a pattern in the arrangement of galaxies themselves. On the largest scales, the universe has a structure, a vast cosmic web. Galaxies are not scattered randomly like grains of sand tossed on a floor, but rather arranged along filaments and clumped in nodes, with huge voids between them. Imagine a three-dimensional spider web, or the filigree of frost on a window pane, or the neural connections in a brain. The universe's galaxies trace similar patterns. There are regions where hundreds or thousands of galaxies cluster together in a knot, connected by long filaments of galaxies stretching outwards. Between these filaments lie enormous voids, spherical or elongated regions, spanning tens of millions of light-years, that contain only a few galaxies or none at all. This is the cosmic web, the large-scale skeleton of our universe. How did this web form? In the early universe, matter was almost uniformly spread, with tiny, denser spots and slightly emptier spots. Over billions of years, gravity amplified those slight differences. The denser spots grew denser as they pulled in matter from their surroundings. The emptier regions grew emptier as matter flowed out of them toward the denser attractors. With time, a foam-like pattern emerged. The densest seeds became clusters of galaxies. Matter flowed along filaments into these clusters, like rivers feeding lakes. The voids in between emptied out more and more. We ended up with this intricate structure, a lace of galaxy clusters and groups connected by bridges of matter, outlining cavernous voids where few stars shine. Intriguingly, this arrangement seems to be guided by an invisible hand. Dark matter. Dark matter, the mysterious substance that neither emits nor absorbs light, makes up the bulk of the matter in the universe, about 85% of it. It was dark matter's gravity that began the collapse of matter into filaments and nodes. Simulations of the universe's evolution, when they include a vast halo of dark matter particles, show the emergence of a cosmic web strikingly similar to what large telescopic surveys observe. It is as though dark matter provided a hidden scaffolding, and ordinary matter, the gas that formed stars and galaxies, followed that scaffold, outlining it with luminous points. We have even caught glimpses of this web. Astronomers using giant telescopes have mapped the positions of galaxies by the millions, revealing filaments and voids across billions of light-years. In surveys, they have identified colossal structures like the Sloan Great Wall, a filament of galaxies about 1.4 billion light-years long, and vast empty regions like the Boötes Void, an enormous spherical gap, roughly 330 million light-years across, containing far fewer galaxies than expected. These names sound abstract, but they underscore how huge and structured our cosmos is. In one striking image, a faint bridge of hydrogen gas, illuminated by distant quasars, was observed stretching between galaxies in the early universe, exactly where models predicted a filament of the cosmic web. The pattern of filaments and voids has become unmistakable. Astronomers speak of this cosmic web as the most fundamental, large-scale structure of our universe. If you could travel magically fast and hover outside the universe, you would see this network glowing faintly. The clusters shining bright, where hundreds of galaxies clump together, the filaments as luminous strands between them, and the voids as vast black hollows. It would look somewhat like a network of veins or the synapses of a giant mind, though on an inconceivable scale. This is the architecture of the cosmos, a tapestry woven from gravity and time, with dark matter as the loom. Where filaments intersect, galaxies gather. Where filaments stretch out, galaxies line up like pearls on a string. And in the enormous voids, we find nearly pure space, the closest thing to nothing that nature allows, bounded by the walls of this cosmic honeycomb. Even as gravity pulled matter into this cosmic web, Another process was at work on the grandest scales, the expansion of space itself. Since the Big Bang, space has been stretching, carrying galaxies with it like chips of wood embedded in a rising tide. In the early universe, this expansion was furious. Later it slowed, as the mutual gravity of galaxies tugged against it. One might imagine a fireball explosion that initially hurls shrapnel outward rapidly, then slows as debris feels drag or gravitational pull. For a long time, astronomers thought that gravity might eventually slow the expansion to a stop or even reverse it into a collapse. But to our surprise, the expansion never halted. In fact, it began to speed up. About 5 or 6 billion years ago, a time when our own sun was still young, the universe's expansion started accelerating. Distant galaxies began receding from each other faster and faster. Some force or energy woven into the fabric of space was overpowering gravity on cosmic scales. We call this mysterious agent dark energy. Its nature is one of the biggest puzzles in science today. We observe its effects. It makes up roughly 70% of the total energy content of the universe and is smoothly distributed throughout space, not clumped like matter. It acts as a sort of anti-gravity, a pressure inherent to empty space that pushes outward. One way to think of dark energy is as a property of space itself. As space expands, new space comes into being, and with it, more of this repulsive energy. It's as if the very fabric of the cosmos has an inbuilt tendency to stretch, a subtle springiness. This is why distant supernovae appear dimmer than expected. They are farther away than they would be in a universe slowing down. The light had to travel a greater distance, and thus time, because the space between here and there expanded more while it was en route. Multiple lines of evidence, from those supernova measurements, from the patterns imprinted in the cosmic background light, from the distribution of galaxies, converge on this truth. The expansion is accelerating under the influence of something invisible and pervasive. What is dark energy? We do not yet know. It could be the zero-point energy of the quantum vacuum we talked about earlier, the residual energy of empty space, scaled up to cosmic proportions. If that's the case, it is essentially Einstein's cosmological constant come to life, a constant energy density filling space. Or dark energy might be a new kind of field, a dynamical energy that changes over time, sometimes called quintessence. Some even speculate about exotic possibilities. Perhaps dark energy hints that our understanding of gravity is incomplete on the largest scales, or that our universe interacts in subtle ways with others. These ideas remain speculative. For now, dark energy behaves, as far as we can tell, like a constant, a steady background push making the universe expand faster and faster. So what does this mean for the future? If dark energy remains dominant and roughly constant, the universe will keep expanding faster indefinitely. Over immense times, galaxies outside our local group will slip beyond our cosmic horizon, their light stretched and weakened until they effectively disappear from view. The night sky will, in the extremely far future, grow emptier as only the closest galactic neighbors remain visible. Dark energy is like a gentle yet inexorable wind pushing the cosmic web apart. It fights against gravity's effort to congregate matter, and on the largest scales, it wins. The ultimate fate of the cosmos depends on dark energy's nature. Will this acceleration continue forever, leading to an ever colder, lonelier universe? The data so far suggest yes, though we cannot be entirely certain. Some speculative scenarios. If dark energy were to grow in strength over time, a doomsday scenario dubbed the Big Rip, eventually even galaxies, stars, planets, and atoms could be torn apart, billions of years hence. Conversely, if dark energy is not perfectly constant but decays, the expansion might slow or even halt in the far future, perhaps leading to a cosmic turnaround or collapse, Big Crunch. Right now, Evidence points to dark energy being consistent with a constant energy of space, meaning a slow drift toward an ever sparser cosmos, sometimes called a heat death. But these are far future possibilities, tens of billions or trillions of years ahead, far beyond human timescales. In any case, the discovery of dark energy in the late 20th century was a humbling reminder that space holds secrets far beyond our reckoning. Just when we thought we understood the grand motions of the cosmos, the universe unveiled a new twist. The expansion can accelerate, driven by a hidden energy in the void. Space, once again, proved to be not passive emptiness, but an active agent with its own properties and dynamics. We have spoken of dark matter's role in shaping the cosmic web. But dark matter's influence is equally crucial on the scale of individual galaxies and clusters. It is often called the universe's silent majority, unseen yet dominant in mass. While dark energy governs the universe's expansion, dark matter governs the clumping of structures within it. When we look at a spiral galaxy like our Milky Way, we see a rotating disk of stars, gas, and dust. The visible stars amount to only a small fraction of the galaxy's mass. We know this because of how the galaxy rotates. Stars in the outer parts of the Milky Way orbit the galactic center much faster than they would if only the visible matter's gravity held them in. If we count just the stars, gas, and dust that we can see, the outer stars should drift away, unable to hold on at such speeds. Yet they remain bound, as if an enormous hidden mass is providing the extra gravitational pull. That extra mass is dark matter. Dark matter surrounds galaxies in a vast halo extending well beyond the visible edge. In our galaxy, the luminous disk of stars is maybe 100,000 light-years across, but the dark matter halo might span 600,000 light-years or more. This halo is roughly spherical, perhaps slightly squashed, enveloping the galaxy like an invisible cocoon. It's sparsest at the edges and densest toward the center, but even in the center, dark matter passes through ordinary matter almost ghost-like, rarely interacting except through gravity. Thus, every galaxy sits in the heart of a heavy, unseen cloud of dark matter. The stars are like dust caught in a gravitational well created by this invisible mass. We cannot see dark matter directly. It emits no light, no radiation we can detect. We infer its presence solely from its gravitational effects. Beyond galaxy rotation speeds, another strong piece of evidence comes from clusters of galaxies. Clusters are collections of hundreds or thousands of galaxies bound together. Observations as far back as the 1930s noted that galaxies in clusters move too rapidly to be held together by the gravity of visible matter alone. Later, X-ray observations found that clusters are filled with extremely hot gas, which itself outweighs the visible galaxies. Yet even gas plus galaxies wasn't enough to explain the gravitational glue. Again, dark matter provided the answer. Furthermore, clusters, and even galaxies, act as gravitational lenses, bending and distorting the light from background galaxies into arcs and rings. By analyzing these lensing patterns, we can weigh the cluster and map where the mass lies. These maps invariably show far more mass than can be accounted for by luminous matter and distributed in a diffuse halo. In some famous cases, such as the Bullet Cluster, the collision of two galaxy clusters, we see that the stars of the clusters passed through each other relatively unscathed. The hot gas slammed into each other and slowed, giving off X-rays. But the bulk of the mass, inferred from lensing, sailed through with the stars. This suggests the dark matter did not collide like the gas did. It passed through, interacting only via gravity. It's a cosmic demonstration that dark matter is a distinct component, not just hidden ordinary matter. What is dark matter? Much like dark energy, it remains unknown in composition, though its behavior is less exotic in many ways. It clumps under gravity, for instance. It could be a new kind of particle, perhaps something like an invisible cousin of the neutrino, a particle that rarely interacts. Experiments deep underground and in space are trying to catch the faintest whispers of dark matter particles streaming through Earth. So far, they have only narrowed the possibilities, not conclusively found them. Another clue comes from the early universe. Subtle patterns in the cosmic microwave background and the abundances of light elements tell us dark matter is not made of protons and neutrons, baryons, the stuff of atoms, but something else that did not interact with light or normal matter in the early hot universe. For now, dark matter remains a silent partner. It neither shines nor blocks light, but it shapes the universe on every level. Without it, galaxies as we know them might not have formed or might fly apart. With it, they coalesced and hold together. Our own existence likely owes to dark matter's stabilizing gravity. Without the enormous hidden halo of the Milky Way, our galaxy's spinning disk might not have stayed intact for billions of years, for life to develop in a stable environment. This ghostly matter is almost a spiritual presence in a scientific sense. Omnipresent, yet invisible. Influential, yet elusive. One cannot help but feel a sense of mystery and respect, knowing that when we look out at the night sky, most of the mass shaping the glittering patterns of stars and nebula is invisible to our eyes. Among the most startling outcomes of gravity's ability to warp space are black holes, regions where space turns so steeply inward that not even light can climb out. Black holes are space gone rogue. Gravity run amok to the point that a massive star's core, or any sufficiently dense mass, collapses virtually to a point. They are the graveyards of massive stars, and perhaps the seeds of new cosmic structures. In a sense, black holes are where space itself falls inward, dragging anything nearby with it. Imagine a star many times heavier than the Sun, burning its nuclear fuel fiercely over a few million years. Eventually, the fuel runs out, and the core collapses under its own weight. If the star is massive enough, more than about 20 times the Sun's mass initially, no force in the universe can halt that collapse. The core implodes. Electrons and protons crush together to form neutrons, as in a neutron star, but even neutron pressure fails if the mass is too great. Gravity wins completely. The core continues collapsing past any known state of matter, and a black hole is born. All the star's mass is now contained in an infinitely small point, according to classical theory, at the center of a region of radically curved space. Surrounding that point is an invisible boundary called the event horizon, the point of no return. Once anything, matter or light, passes inside the horizon, it cannot escape back out. To an outside observer, the event horizon is essentially the black hole's surface, though it's not a tangible surface. It's the radius at which escape velocity equals the speed of light. For a star-sized black hole, this horizon might be only a few kilometers across, even though it contains a mass several times that of the Sun. Imagine the Sun crushed down to the size of a city. That's the kind of density and curvature we are talking about. Inside the event horizon, space and time themselves trade roles in a strange way. Falling towards the center is as inevitable as moving forward in time. All possible paths lead deeper in. What lies at the very center? General relativity says a singularity of infinite density, but in truth, our physics breaks down there. Quantum gravity, the unification of quantum mechanics and gravity that we haven't solved yet, would be needed to understand it. Perhaps there is a tiny warped region, or even a bridge to elsewhere. Speculative ideas like wormholes have been imagined lurking in these depths, but evidence is lacking. From outside, what we see of a black hole is not the hole itself, which emits no light, but its effects on the surroundings. Gas spiraling into a black hole heats up and glows brilliantly in X-rays just before crossing the horizon. If the black hole is feeding, we often see an accretion disk of superheated matter and sometimes jets of particles shooting out at nearly light speed from the poles, powered by the hole's magnetic and rotational energy. But the clearest signature is gravitational. We observe stars orbiting an invisible mass, as in the center of our own Milky Way, where stars whip around a dark center at thousands of kilometers per second, indicating a mass 4 million times that of the Sun confined in a space smaller than our solar system. Nothing but a black hole could do that. Indeed, we are now certain that a supermassive black hole anchors most, if not all, large galaxies, including ours. Only recently, humanity captured its first image of a black hole's immediate vicinity, a glowing donut-shaped ring of light surrounding a dark shadow in the core of galaxy M87, about 55 million light-years away. This shadow was the silhouette of the event horizon's influence, the closest we can come to seeing the unseeable. It affirmed that our concepts of these cosmic abysses are not mere math fiction. They are real. Black holes come in different sizes. Stellar black holes form from collapsing stars and weigh a few to dozens of suns. Supermassive black holes, millions to billions of solar masses, reside in galactic centers. They likely grew by consuming stars and gas and merging with other black holes over billions of years. We've even found middling black holes, intermediate mass, and speculate tiny primordial ones might have formed in the early universe. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, indiscriminately sucking everything in. An object can orbit a black hole safely from a distance, much as it would orbit any mass. Only when you venture too close, within the horizon, is escape impossible. However, the extreme environment near a black hole can shred stars via tidal forces and power those spectacular jets and high-energy radiation that can stream outward for thousands of light-years. Black holes push physics to its limits. They represent space curved to an extreme and time slowed to a crawl at their threshold. If you watched a clock falling toward a black hole, you'd see it tick slower and slower as it neared the horizon, never quite appearing to pass through. It would fade and redshift to darkness. Meanwhile, the clock itself, were it indestructible and could fall in, would experience time normally and cross the horizon without fanfare, only to meet whatever fate awaits inside. It's as if the fabric of space-time gets so warped that it pinches off a region from causal contact with the rest of the universe. That pinched-off region is the black hole's interior, a kind of cosmic oubliette, a place where information goes in and, according to our best understanding, cannot come out. This raises deep questions about the nature of information in physics, the black hole information paradox, which physicists are still debating. In addition, theory predicts that black holes aren't completely black. They can emit a very faint glow of particles due to quantum effects at their horizon, a phenomenon called Hawking radiation. Over mind-boggling spans of time, black holes can slowly evaporate by this process, one trickle of radiation at a time. A black hole the mass of the Sun would take far longer than the current age of the universe to evaporate. So this effect is negligible for now, but for the smallest black holes it could be significant. It ties into the information paradox as well. If black holes eventually vanish, where does the information about what fell in go? Does it come out in the Hawking radiation in scrambled form? These questions show how black holes force us to unite principles of quantum mechanics and relativity in our quest for answers. Thus, black holes sit at the intersection of the cosmic and the quantum, teaching us about gravity, thermodynamics, and the limits of knowledge. In a more poetic sense, black holes are like the universe contemplating its own depths. They are the night within the night, a darkness so absolute that it challenges our notions of space and existence. They remind us that space can fold in on itself and create edges to reality, boundaries beyond which we cannot see or know. They are not just holes in space, but holes in our understanding, calling to us with mysteries. And yet, they are also integral to the cosmos. By merging and growing, they release energy and shape galaxies, perhaps even triggering new star formation via their outflows. Even in their silence, they influence the grand design. Space, turned inward upon itself, creates these paradoxical objects where end and beginning blur. In the vicinity of a black hole, one truly feels that the line between nothingness and something has thinned to its limit, a fitting extreme in our journey through the realms of space. For all the wonders that fill space, there is a fundamental limit to how much of the universe we can see or ever influence. We call this limit the observable universe, the sphere around us, beyond which light has not had time to reach us in the almost 14 billion years since the Big Bang. It's as if we are inside a glowing bubble, where the glow marks the farthest things we can observe. Beyond that horizon, there may be more galaxies, more space, perhaps an infinite expanse, but they are, for now, and likely forever, out of reach. This cosmic horizon exists because the universe is finite in age, and light has a finite speed. Think of standing in a vast plain shrouded in fog. You see a circle around you up to a certain distance where the fog becomes opaque. You suspect the plane continues beyond, but you cannot see it. Our cosmic fog is simply the fact that beyond a certain distance, light hasn't yet arrived, or has been stretched and dimmed beyond detection. At the edge of our vision lies that afterglow of the Big Bang, the cosmic microwave background, which acts like a bright wall of light from 380,000 years after the universe began, beyond which we cannot see with light, because earlier the universe was opaque. That shell of light is currently about 46 billion light-years away in all directions, much farther than 13.8 billion light-years, because space itself expanded while the light traveled. That defines the radius of our observable universe. It is humbling to realize that no matter how advanced our technology becomes, we cannot obtain information from beyond our cosmic horizon by any normal means. Those regions are not just far away in space, they are effectively unreachable in time. Their light may only arrive far in the future, or perhaps never, if cosmic expansion carries them away faster than light can bridge the gap. In an accelerating universe like ours, there are galaxies right now on the edge of visibility that will eventually fade away as well. The horizon of our observable universe can, in fact, shrink in terms of what remains visible in the far future. This means our observable universe is a dynamic thing. Over cosmic time, new regions become observable as their light finally arrives, while very distant regions slip beyond view. However, from our standpoint today, we have a vast observable universe to explore with our minds. It contains an estimated 2 trillion galaxies, each with billions of stars. Within the 93 billion light-year diameter sphere, we can, in principle, observe. That number boggles the mind, yet it might be only a small fraction of the whole universe if space extends far beyond what we can see. We must accept that there is a horizon to our knowledge, an edge beyond which we cannot peek, at least not with light or signals as we understand them. The existence of this horizon also reminds us that our place in the universe is not central in a spatial sense. Every observer, wherever they are, has their own observable bubble of similar radius centered on them. An alien in a galaxy billions of light-years away sees its own cosmic microwave background and horizon, overlapping with ours in some regions, but including parts of the universe we cannot see and excluding parts we can. It's a bit like being in the middle of an ocean. You see the circle of the horizon around you, but you know the ocean continues beyond. We float in the cosmic ocean, seeing a sphere of sky around us, but the cosmic ocean itself likely stretches well past that boundary. Sometimes, in our imaginations, we wonder, what lies beyond that horizon? More galaxies receding forever? Perhaps parts of the universe with different properties? Or simply an endless stretch of more darkness and light? We don't know, and perhaps cannot know. Yet we can be grateful that we can see as much as we do, a glorious expanse of space and time, nearly 14 billion years deep. Within that volume, we have uncovered physics that likely applies everywhere beyond as well, giving us confidence that the unseen parts follow the same cosmic story. Our observable universe defines the stage of our cosmic story. It is enormous, yet finite from our perspective. Beyond its curtain lies mystery. This horizon of visibility is a gentle reminder of our limitations. It tells us that no matter how much we strive, there will always be something just out of reach, a frontier that recedes as we chase it. And perhaps that's for the best. An infinite universe with finite observation keeps us always wondering, imagining, and pushing to understand what might lie beyond the next horizon. Now, let us drift away from all these structures, beyond the warm lights of galaxies and the faint gauze of clusters, into the great dark in between. This is intergalactic space, the expanse between galaxies. Here, in the middle of a vast cosmic void, you would find yourself in nearly perfect silence and solitude. No nearby stars, no nebulae, likely not even a single atom in the volume of your body. The nearest galaxy might appear as just a tiny smudge of light, or perhaps nothing visible to the naked eye at all. You are as alone as one can be, surrounded by a blackness almost undisturbed by any glimmer. This is the closest thing to nothingness the universe offers on a macro scale. Intergalactic space is not completely empty, but it comes impressively close. In the most rarefied voids, there may be only a handful of atoms in an entire cubic meter of space. Imagine an area the size of your living room containing perhaps a few stray hydrogen atoms and maybe a single photon passing through. For all intents and purposes, it is a vacuum better than anything we can create on Earth. No sound can travel here. Sound requires a medium like air or water, and here there is effectively none. If you were somehow alive and unprotected in this environment, setting aside the impossibility of no air and extreme cold, you could scream, and no one would ever hear even the faintest whisper. The concept of noise simply does not apply. It is a cathedral of silence. The darkness is equally profound. Far from any star, you would see blackness in all directions. Perhaps, if your eyes were sensitive enough, you'd catch the faint collective glow of distant galaxies as a weak background light, much like the Milky Way band appears from a dark Earth location, but far dimmer. And of course, the universe is filled with light of wavelengths our eyes cannot see. Infrared, microwave, radio waves, even the cosmic microwave background radiation permeating every inch of space at a temperature of 2.7 K, just above absolute zero. But to human senses, intergalactic space feels utterly dark. It's not the kind of darkness we find in any earthly night, where usually some starlight or airglow exists. It's a nearly perfect black, limited only by the faintest glow of faraway galaxies and that omnipresent microwave whisper. In this void, time itself marches on in isolation. A clock would tick just fine, in fact, slightly faster than on Earth, since it's far from any significant gravity, but nothing marks the time. Days and nights have no meaning without a nearby star. A human being would soon lose track of all sense of time, with no external cues, only the steady beating of their own heart, which too would eventually feel deafening in the absolute quiet. Intergalactic space can be thought of as the universe's great wilderness. Just as deserts and open oceans on Earth are sparsely populated, the cosmic voids are deserts of matter. Yet like those terrestrial emptinesses, they have a stark beauty and significance. They are the canvas on which galaxies are arranged. Their emptiness defines the walls of the cosmic web's rooms. They also contain mysterious cosmic rays and tenuous gas that, while incredibly dilute, stretch over enormous volumes and over cosmic time, can influence galaxies when that gas slowly drifts into them or gets ignited by shocks. And though seemingly void, this space is crossed by intangible messengers. Neutrinos emitted by distant supernovae zip through these voids, hardly ever interacting with anything. Gravitational waves pass by, distorting distances by tiny fractions as they go, unimpeded by the lack of matter. The void is the highway of light and gravity across the cosmos. It is the medium through which information of cosmic events travels. One might say that even in emptiness, there is connection, an invisible thread of forces and particles in transit, binding the cosmos together, however tenuously. The emotional weight of such loneliness is hard to fathom. When we send spacecraft out beyond Pluto into interstellar space, which is still far denser than truly intergalactic space. We marvel at them entering deep space, but even they are still within our sun's sphere of influence, surrounded by traces of the solar wind. True intergalactic space lies far beyond, where the influence of any single galaxy is faint. It is a stark reminder of the vast separation the universe imposes between islands of matter. If one were to travel between galaxies, centuries or millennia of traversing nothing await. Yet this nothing is not frightening in the cosmic perspective. It's peaceful and sublime. It's the backdrop that makes the bright islands of stars all the more precious and brilliant. In the great cosmic voids, one confronts the reality of a universe mostly made of darkness and silence. But instead of seeing it as bleak, we might see it as serene. It is the quiet on the canvas that allows the lights of galaxies to stand out. It is the stillness that lets the song of creation, the stars and galaxies and life within them, be heard. The isolation of intergalactic space also carries a philosophical lesson. We, living on a cozy planet in a bustling solar system in a sprawling galaxy, are sheltered from this extreme loneliness by layers of structure and community in the cosmos. We have the warmth of our sun, the protective bubble of our heliosphere, the gentle glow of the Milky Way in our night sky. Only when we venture far beyond do we find the true void. It is out there, immense and indifferent. But from that emptiness, we also came, and to it, if we journey far enough, we return, carrying the spark of life into the dark and filling the void with meaning by our presence. Up to now, we've spoken much of space, the vast distances and structures, the emptiness and connections. But space has an inseparable partner, time. Together they form the fabric of space-time. And just as space is not absolute or fixed, neither is time. The flow of time can stretch, bend, and even nearly stall under the right conditions, intimately entwined with space. Modern physics has revealed that time is relative. A moving clock ticks slower than a stationary one from the stationary perspective, and a clock deep in a gravitational field ticks slower than one in open space. This isn't just theory, it has been measured. Time dilation is a daily consideration in technologies like GPS satellites high above Earth. They tick a bit faster due to weaker gravity and a bit slower due to their high speed. And both effects must be accounted for so that navigation on Earth remains accurate. Consider a scenario. Twins, one stays on Earth, the other takes a fast spaceship to a distant star and back. Upon reuniting, the traveling twin will have aged less than the twin who stayed behind. Perhaps the traveler experienced only 5 years while 10 years passed on Earth. This is not science fiction, but a result of the geometry of space-time. High-speed travel makes the traveler's path through time lean more towards space, distance traveled, and less through time, so to speak. They age less. This is called time dilation due to motion, special relativity, and it has been confirmed with subatomic particles in accelerators and with precise atomic clocks on fast jets. Similarly, imagine a clock at the top of a mountain and another at sea level. The clock at sea level, deeper in Earth's gravity, will tick slightly more slowly than the one at altitude. This gravitational time dilation has also been measured. It's tiny for Earth's gravity, nanoseconds of difference, but near something like a neutron star or black hole, it becomes dramatic. If you hovered just outside a black hole's event horizon, your time might be so slowed relative to the outside universe that a few minutes for you could equate to years or centuries passing for distant observers. This scenario, though exaggerated, was popularized in fiction, but it's grounded in real effects. What does it mean that time can bend? It means that simultaneity, what events happen at the same time, is not universal, but depends on motion and gravity. It means that cause and effect can get tricky if one isn't careful with reference frames. Yet, the speed of light and the structure of space-time preserve a causal order. Nothing can go back in time to create a paradox, as far as we know. It simply changes our intuitive Newtonian idea that time flows equably for all. Instead, each observer carries their own clock, and that clock's readings depend on the observer's path through space-time. Even our everyday life experiences a touch of this. Someone living at high altitude ages a few microseconds faster over a lifetime than someone at sea level. Astronauts orbiting Earth at 28,000 km/h experience time a tiny bit slower due to speed and a tiny bit faster due to being higher up, less gravity. The net effect is they age just a hair less than people on Earth. After a year in orbit, an astronaut might be milliseconds younger than an Earthbound twin. Imperceptible, but real. Time is sometimes visualized as another dimension like space. Just as one can walk different routes through space, one can take different routes through space-time that result in different amounts of time experienced. However, unlike the spatial dimensions in which we can move freely, forward, back, left, right, up, down, time for us has a direction, ever forward. We can move slower through it, relative to others, by moving fast or hanging out in strong gravity, but we cannot turn around and go back. Space offers many possible paths, but time's arrow points one way for all of us, likely linked to the thermodynamic arrow, entropy increasing, that gives time its direction. The intertwining of time and space means that a curved clock is a reality. Clocks follow the curvature of space-time. Wherever space is warped, time is warped too. So a curved clock might be an image of a clock near a massive body being literally influenced by that warping. For instance, a clock on a satellite orbiting Earth is in slightly differently curved space-time than one on Earth's surface, and they diverge unless we adjust them. In essence, every massive object is like a slight break on time in its vicinity. We all live in the little dips in time created by Earth's mass, making our time run imperceptibly slower compared to far-off space. We don't notice because all our human reference points are similarly affected. Philosophically, this relativity of time can be both unsettling and awe-inspiring. It suggests that time is part of the physical fabric, not an immutable backdrop. It means the universe has a personal relationship with each traveler. Your time is yours, mine is mine, and they can differ, yet both are correct for each of us in our own frame. We carry our slice of space-time with us. And though we can't help but move forward in time, we have found ways to manipulate our experience of time by how we move in space or where we situate ourselves. In the cosmic context, understanding time's malleability allows us to navigate the universe more wisely. It tells us that extremely advanced spacefarers, if they ever exist, might exploit time dilation for long journeys, putting themselves in a slower time stream relative to home to make a long voyage more bearable subjectively. It also tells us that near black holes, time gets so bent that one could, in principle, see far into the future of the outside universe while only a short time passes for them, though retrieving that person would be another issue. Everywhere in space, time is quietly varying, slightly different on a mountain than in a valley, slower in Jupiter's gravity than in Earth's, slower still near the Sun. Our universe is a collection of all these personal times, woven together by light signals into a consistent tapestry, but each thread has its unique pace. When you next look at a clock, consider that its ticking is not absolute. Out in space, that same second might stretch or shrink depending on motion and gravity. Time flows like a river, but it can meander, speed up, or form eddies. This is part of the wonder of space-time, a medium so supple that not only can distances shift, but durations can too. Space holds time within it, as a melody holds rhythm, each shaping the other. Our journey through space and time so far has been one of the mind's eye. But there came a moment in our history when space stopped being only a concept out there and became a place we could physically touch. For eons, we were earthbound, looking up and dreaming. Only in the last brief blink of our existence have we reached our hands into the sky and felt the void beyond our world. the first steps were indirect. We built machines to fling into space. In the mid-20th century, a silvery sphere with small antennae was launched beyond the atmosphere, circling Earth. That first artificial satellite was humanity's opening note in the song of space. It carried no life, just a radio beacon, but it proved we could leave our cradle. Soon after, living creatures, and then humans themselves, rode fire and thunder to break the bonds of gravity. When the first person orbited Earth, they became a tiny moon to our planet, experiencing weightlessness and the black sky above our atmosphere. In those moments, space was no longer an abstract void, but a real place where a human heart could beat. Courageous explorers flew in cramped capsules and winged spaceplanes, trusting their lives to thin metal shells that separated them from deadly vacuum by mere inches. They saw with their own eyes the curvature of Earth against the black of space, and stars that do not twinkle, for there is no air up there to make them shimmer. Then came one of humanity's defining moments, setting foot on the moon. Our natural satellite, a piece of the cosmic neighborhood, was reached by human explorers. When they stepped onto the grey, dusty regolith, the boundary between Earth and space was profoundly crossed. For the moon is a world in space, with no air and an alien sky. Standing there, an astronaut saw Earth not beneath their feet, but hanging in the sky, a blue marble suspended in darkness. In that instant, space wasn't just something around us. It was the ocean in which two worlds, Earth and moon, floated, and a human stood on one looking at the other. The footprints left on the lunar surface are still there, undisturbed in the silent vacuum. They may last millions of years. In that sterile, airless environment, those prints are a message frozen in time. We were here. We came from another world. Meanwhile, we began populating near-Earth space with satellites of all kinds, for communication, for navigation, for studying Earth's weather and climate, and for peering out into the universe. Our planet became encircled by a shell of human-made moons, sending radio signals and digital information around the globe. At the same time, we built robotic probes to visit other planets, becoming our emissaries to places we cannot yet go ourselves. We sent orbiters and landers to the Moon, Mars, Venus, Jupiter, Saturn, and beyond. We have touched the surface of Venus with a lander, which survived only moments in its hellish heat, and of Mars with rovers that roam for years. We have even sent probes sailing out of the solar system entirely, carrying golden records etched with sounds and images of Earth, like a cosmic message in a bottle. To truly extend our senses, we also placed telescopes above our blurring atmosphere. These orbital observatories, free from the distortion of air, began to show us the cosmos in unprecedented detail. Famous space telescopes revealed star-forming nebulae as great cosmic landscapes, surveyed distant galaxies, and even measured the age of the universe with precision. They also looked back at Earth, underscoring how thin and precious our livable atmosphere is, and how alone our blue world seems against the black backdrop. Each telescope and probe is like a stretching of our nervous system into space, a way to feel and see beyond our natural reach. In low Earth orbit, we assembled a large space station, a habitable artificial world where, since the dawn of the 21st century, humans have lived continuously, conducting science and learning how to survive off-planet. This orbiting laboratory is a symbol of international cooperation and a beachhead for future space endeavors. Astronauts aboard see 16 sunrises and sunsets each day as they circle the globe every 90 minutes. They float in microgravity, adapt to an existence where up and down have little meaning. From their vantage, they see Earth as one borderless realm and space as an endless expanse beyond. They are inhabitants of the space between worlds, a small step toward living continuously in that frontier. Each of these achievements, satellites, moonwalks, space stations, interplanetary probes, space telescopes, is a thread stitching humanity into the fabric of space. No longer are we mere observers. We have become participants. We have left footprints on another celestial body, extended our eyes to the far reaches of the cosmos, and even sent objects beyond the solar system. We have touched space and been touched by it. Who can forget the poignant sight of Earth rising above the moon's horizon, or the breathtaking images of Saturn's rings backlit by the sun, or a deep field photograph showing a swarm of galaxies billions of years old in a patch of sky no bigger than a grain of sand? These moments expand our perspective, making space not just an abstraction, but a place we know, even if vicariously. We carry the dreams of past generations who gazed up in wonder, and we prepare the way for future generations who will go farther still. Leaving Earth, even temporarily, changes a human being. In microgravity, the near weightlessness of orbit, astronauts experience both wondrous freedom and profound physical challenges. Their bodies, evolved over millions of years to work against gravity's pull, must adapt within days to its near absence. This adaptation is fascinating and instructive, showing how intimately we are tied to Earth's environment and how we might adjust to new ones. One of the first things astronauts notice is the relief from weight. They can lift heavy equipment with a fingertip, float effortlessly from one end of their spacecraft to the other. It's like an endless dance or flight. Many speak of the joy of drifting, the childlike play of somersaults in midair. But microgravity also causes bodily fluids to redistribute. Blood and water that are normally pulled to our legs by gravity now move upward. Faces become puffy, legs slim. Astronauts often feel congested, as if hanging upside down. This fluid shift can also alter eye shape and pressure, causing some to need glasses in orbit or have vision changes that sometimes persist after return. Without gravity's constant tug, bones and muscles no longer bear weight. As a result, they begin to weaken. We have learned that astronauts can lose 1 to 2% of their bone density per month in space, especially in weight-bearing bones like hips and legs, an extreme, accelerated osteoporosis. Muscles, too, atrophy, particularly the postural muscles that help us stand upright. To counter this, astronauts must exercise vigorously for a couple of hours each day using resistance machines and cycling or treadmill devices. They often must be strapped down so they don't float away while running. Exercise helps reduce the loss, but some bone thinning and muscle shrinkage still occur. After a long mission, astronauts return to Earth temporarily weaker, and it can take weeks or months of rehab to rebuild what was lost. Interestingly, astronauts often grow a bit taller in space, by a few centimeters, because without gravity compressing the spine, the vertebrae separate slightly. They enjoy being taller for a while, but this can also cause back pain as the muscles supporting the spine must stretch differently. The heart, not having to pump blood uphill from the feet as much, can weaken and change shape slightly. It becomes more spherical and may decrease in volume output. The longer-term effects of this are still being studied. Also, the balance system in our inner ears, which uses fluid and tiny hairs to sense orientation, gets confused without a gravity reference. Many astronauts experience space adaptation syndrome, motion sickness, for the first couple of days, nausea, dizziness, as their brains recalibrate to a world where down is no longer meaningful. Once adapted, their vestibular systems essentially tune out the gravity reference, and they move quite adeptly in 3D, able to work on any wall or ceiling as easily as a floor. Living in confined quarters for months poses psychological and social challenges as well. Astronauts miss weather, rain, wind, the feeling of sun on skin. They have sunlight through windows, but not the breeze. They miss certain foods. Fresh fruits and vegetables are a delicacy when supply ships arrive. They are extremely busy, which helps, but they're also isolated from normal life, with only emails or occasional video calls home. The camaraderie with crewmates and the sense of mission help keep them mentally healthy, but every astronaut feels the absence of Earth in subtle ways. The smell of soil and trees, the sound of birds, the presence of family. It is the sacrifice they make to push into the frontier. Yet, there are profound positive transformations as well. Many astronauts describe the overview effect, a cognitive shift when seeing the whole Earth from space. They see our planet as one borderless orb, fragile and beautiful against the black void. This often instills a deep sense of interconnectedness and a desire to protect our home world. Some speak of it in spiritual terms, a near transcendent experience of seeing Earth in its entirety and realizing the unity of humanity and the thinness of the atmosphere. This perspective shift is a psychological transformation unique to spacefarers, and it is considered one of the most powerful effects of space travel on the human mind. On the space station, astronauts also carry out tasks that change their relationship with mundane things. They learn to eat by chasing floating blobs of water or juice and capturing them in their mouths, or by carefully sticking their food packages to surfaces with tape so they don't drift away. They sleep in sleeping bags tethered to a wall or ceiling, enveloped so they won't float and bump into equipment. Some say sleeping in microgravity, without a mattress pressing against you, feels like curling up in mid-air. Odd at first, but eventually comfortable, like being cradled by space itself. They also find that their sense of time can shift. With 16 sunrises a day, they rely on clocks and scheduled night periods with window shutters closed to simulate day-night cycles for their body's rhythms. Over longer durations, the question arises, could the human body adjust more permanently to microgravity or partial gravity, like the 0.38 g on Mars? Would children born in such environments develop differently? We have some data from astronauts spending a year or more in orbit, which show that extended microgravity largely continues the same trends of bone loss and muscle adaptation, eventually reaching a new lower equilibrium. The body is resilient and adapts impressively, but certain systems like bone might not fully recover if the duration is too long. We don't yet know the limit. We do know that radiation exposure in space, outside Earth's protective magnetic field, poses serious health issues for longer voyages, as cosmic rays slowly damage cells and increase cancer risk. Future spacecraft and habitats will need better shielding and perhaps medical countermeasures to mitigate this. Perhaps, over centuries, humans living on Mars or other worlds would gradually develop new traits. Taller frames in low gravity, denser bones to resist bone loss, altered circadian rhythms to match their world's day length. They might become somewhat distinct branches of humanity, shaped by their environments. If one day people dwell in free-floating space habitats with artificial gravity, or even in microgravity for generations, they too might adapt uniquely. In this way, the human story could diverge across space, each population molded by its new home. We're far from that, but the seeds of it are visible in how quickly and subtly our bodies respond to even short stays in orbit. We've already begun evolving culturally, and perhaps one day biologically, to be a spacefaring species. The transformations, puffy faces, weaker legs, stronger appreciation for Earth's gravity, broadened perspective, are part of the pioneering price and reward. They underscore that when we finally send humans on years-long voyages to Mars or establish outposts on the Moon, we will be changing ourselves as much as the environment. Space does not just permit life, it challenges life to transform, and in doing so reveals what is essential and what can adapt. Having set tentative footsteps beyond Earth, our gaze naturally turns to horizons ahead. What destinations lie within reach for the next chapters of our journey? Mars, for one, has beckoned for generations. So have the Moon's beckoning plains for a sustained return, the resource-rich asteroids, and beyond them, the giant planet's intriguing moons, and then, ultimately, the stars themselves as the far frontier. The Moon is likely our next close step. After the first era of human moon landings, humanity took a hiatus, but plans are well underway to go back, not just to visit, but to stay. The vision is a permanent lunar base, perhaps at the moon's south pole, where ice lurks in shadowed craters. That ice could be harvested into water, oxygen, and even rocket fuel by splitting water into hydrogen and oxygen. A lunar base could serve as a research station, like an Antarctic outpost, studying the moon's geology, testing technologies for living off Earth, and serving as a proving ground for longer missions. It's humbling and thrilling to imagine future explorers waking up in a habitat on the moon, stepping outside in suits to see the Earthrise on the horizon of an airless sky, tending greenhouse plants under low gravity, mining regolith for materials, and practicing the art of survival on another world. Mars, the red planet, has captured human imagination for centuries. Though farther away, a journey of months, it offers a place that in some ways is more hospitable than the moon. Mars has an atmosphere, thin as it is, day-night cycles similar to Earth's, and essential elements like carbon, nitrogen, and water, as ice, accessible on its surface. The draw of Mars is profound. It's a planet that once had liquid water flowing on its surface, and perhaps was warm enough for life billions of years ago. If life ever arose there, traces might remain in the soil or rock. And if life did not arise, Mars presents a canvas for possible future habitation, a second home for humanity, though one requiring domes and life support to sustain us. Plans for Mars involve sending humans in the not-too-distant future. Maybe the first crew will step onto Martian soil within a couple of decades. They would endure a 6 to 9 month voyage through interplanetary space, likely spend a year or more on the surface, exploring and doing science, and then undertake another long journey home. The challenges are immense: exposure to radiation during the trip, the psychological toll of isolation and distance. Earth would shrink to a tiny, star-like point in the Martian sky at times, with radio signals taking 10 or 20 minutes one way, and the need to be largely self-sufficient so far from help. Landing on Mars is no small feat either. Its thin atmosphere is tricky, not enough to slow a spacecraft as easily as Earth's air does, but enough that you can't ignore it. Yet, robotic missions have shown it's doable, and designs for habitats, rovers, and ascent vehicles are on the drawing board. We can imagine that historic day. A human being sets foot on Mars for the first time. The gravity is only a little more than a third of Earth's, so their steps have an odd bouncing lightness. The sky overhead is a butterscotch orange hue, and the sun, though bright, appears smaller and cooler than on Earth. As they look around, they see an empty expanse of reddish desert extending to distant dusty hills. There is no sound except the ones they make. Mars's thin air carries almost nothing. At twilight, perhaps, they will see Earth as a pale blue star winking into view, a tiny beacon of all they left behind. In that moment, all of human history to date will be looking back at them across the gulf of space, and all of humanity's future beyond Earth will be opening in front of them on that silent Martian plain. If and when humans establish a foothold on Mars, it will represent a turning point, becoming a multi-planet species. The first settlers might live in habitats shielded by Martian soil, grow plants in controlled environments, and systematically explore for resources like subsurface ice or useful minerals. Over time, they might build more permanent bases, maybe even attempt small-scale terraforming experiments, though making Mars truly Earth-like would be a project for centuries or millennia, if it's feasible at all. The first child born on Mars would mark a new branch of humanity no longer tied entirely to Earth's cradle. Beyond Mars, the solar system offers other tantalizing targets. There's talk of sending humans to visit asteroids, small worlds which could be rich in metals and water. A mission to an asteroid would test deep space travel techniques and give experience in low-gravity operations. Asteroids could one day be mined to build structures in space, or to obtain water for sustaining space settlements and fueling rockets. Water, being heavy, is expensive to lift from Earth, but abundant in some asteroids. The idea of using asteroids as stepping stones or resource depots takes shape. One can imagine a network of fuel stations in space derived from asteroid mining, enabling easier travel to Mars and beyond. The moons of the outer planets also intrigue scientists and the public. Jupiter's moon Europa hides a deep ocean beneath its icy crust. Saturn's moon Enceladus jets geysers of water into space from another subsurface sea. Saturn's Titan has a thick atmosphere and lakes of liquid methane. These are far, harsh places for humans to reach with current technology, but they tantalize because of their uniqueness and their potential for harboring life, at least microbial life in those hidden oceans under ice. In the far future, one could imagine research outposts orbiting these moons, or even submersible probes someday swimming in Europa's ocean. For now, these remain domains for our robots. Human footsteps on those worlds are likely a very distant dream. Humanity's more immediate future in space likely involves building up infrastructure, space habitats and fuel depots, better propulsion systems, and learning how to utilize what's already out there. In situ resource utilization, as engineers call it. People dream of giant rotating space stations that produce artificial gravity, where hundreds or thousands could live and work, maybe as way stations between Earth and Moon or Earth and Mars. Concepts like massive rotating cylindrical settlements have been proposed to house communities in space in the more distant future, using materials mined from the Moon or asteroids. Such colonies could even have agriculture, parks, and small towns inside spinning megastructures, creating a shirt-sleeve environment in the void. While purely conceptual now, they fire the imagination of what a truly spacefaring civilization might eventually create. If we project progress forward, one can imagine a time where the solar system is alive with human activity. Perhaps lunar mining outposts supply raw materials and fuel, while rotating habitats at Lagrange, points between Earth and Moon, house thousands in simulated gravity. Mars could host bustling research towns beneath pressurized domes, with children who have never felt Earth's heavy gravity running freely under a salmon-colored sky. In the asteroid belt, factories might forge spacecraft from spaceborne metals, and on the moons of Jupiter, laboratories could drill into subsurface oceans in search of alien microbes. Spacecraft, both crewed and robotic, would shuttle along established routes, and way stations would speckle the darkness, making deep space feel a bit more traversable. It would be a future where our species is not bound to one world, where Earthling becomes Solarian, a citizen of many worlds. This may sound like science fiction, but it's essentially an extrapolation of what our ingenuity could achieve with time, resources, and the continued drive to explore. The seeds are already visible in our current ventures. And then there are the stars. Interstellar travel, going to another star system, is the grandest of dreams, currently well beyond our engineering. The nearest star, apart from the Sun, is over 4 light-years away. With chemical rockets, it would take tens of thousands of years to reach even that closest neighboring star. That hasn't stopped us from dreaming and even planning precursors. One idea is to use powerful ground-based lasers to push many tiny, ultralight sails to a significant fraction of the speed of light. These star chips could reach the Alpha Centauri system in a few decades and send back pictures of any planets. It's a wild idea under study, representing an early attempt to make interstellar reach possible, at least for probes within a human lifetime. For crewed flight, proposals often verge on science fiction, generation ships where entire societies live and die during a voyage lasting centuries or millennia, suspended animation or stasis for travelers, or engines that harness exotic physics, like antimatter or fusion drives, to drastically cut travel time. While the stars are distant, they remain a locus of aspiration. Every advance we make, nuclear propulsion, closed-loop life support, faster communications, brings what was once impossible slightly closer to the realm of the possible. One day far ahead, humans, or our AI descendants or engineered successors, might actually embark on journeys to other star systems, perhaps finding new homes around alien suns. The timeline for such ambition is hard to predict, centuries, millennia, longer, but it underscores a fundamental aspect of our relationship with space. We are never content to stay. There is always a next horizon. From cave dwellers venturing over mountains, to seafarers crossing oceans, to astronauts leaving Earth orbit, the unknown beckons. In dreaming of moon bases, Martian colonies, asteroid mining, and interstellar crossings, we carry forward the same wonder that made us look up at the Milky Way in ancient times and weave tales about it. Our modern rockets and probes are our ships of legend. The destinations may no longer be mythic heavens, but real physical worlds. Yet the emotional pull is similar. Space offers an endless frontier that challenges us to grow, technologically, intellectually, ethically. Will we become caretakers of multiple worlds? Will we spread life to barren planets, making gardens in the desert of space? Or will we simply learn to appreciate and safeguard the precious oasis of Earth by seeing how rare and daunting other places are? The dreams of the future run on both practical and romantic rails. Practically, establishing a human presence beyond Earth increases our species' chances of survival if disaster befell our home world, and it opens up vast resources for use. Romantically, it fulfills something deep in our psyche, an urge to explore, to know the unknown, to step beyond boundaries. Space is the ultimate embodiment of those boundaries, and crossing each one is a giant leap for our collective being. As we plan these leaps, from returning to the moon to eventually reaching another star, we do so with a mix of scientific rigor and childlike wonder. It is perhaps the greatest adventure we can undertake, to leave our cradle and see what lies outside, and in doing so, to discover not just new worlds, but new facets of ourselves. Reaching other stars with conventional technology is daunting. But human curiosity doesn't stop at what seems unreachable. It imagines ways to transcend barriers. This is where speculation and cutting-edge physics meet. What if we could cheat the cosmic speed limit or take shortcuts through space-time? What if our universe is not the only one? These questions, once purely philosophical, are now topics of serious scientific hypothesis, though still highly theoretical. They ignite our imagination about what space could allow, under laws of physics we are only beginning to glimpse. One such speculative concept is the wormhole. Envision space-time as a stretchable fabric. A wormhole would be like a tunnel or shortcut through that fabric, connecting two distant points via a shorter hidden path, almost like a secret door in a mansion that lets you jump from one wing to another without walking the long corridor. If such wormholes exist and could be stabilized, a traveler might enter one end and emerge far away, perhaps in another galaxy or even another universe. Wormholes arise as possible solutions in the equations of general relativity under certain exotic conditions. But to hold a wormhole open so it doesn't pinch off, calculations suggest you'd need negative energy or pressure, something not present in ordinary matter in bulk. We've observed hints of negative energy in quantum effects, like the Casimir effect between close plates, but nothing that can be amassed to engineer a traversable wormhole. So for now, wormholes remain hypothetical. They tantalize with the idea of instantaneous cosmic journeys and even time travel, since a wormhole might allow moving backward in time under some setups. But they also warn us with paradoxes. Nature, as far as we know, isn't in the habit of handing out free passes through time and space. There may be fundamental constraints that keep wormholes from being useful or stable. Still, they populate science fiction and theoretical physics papers alike, perhaps the ultimate wild card in the cosmic deck. Another audacious idea is the warp drive, the notion of bending space around a vessel so that it effectively moves faster than light relative to distant observers, without locally breaking the light speed limit. The most famous concept was put forward in the 1990s, a solution of Einstein's field equations suggesting that if you could form a warp bubble contracting space ahead of a ship and expanding it behind. The ship could ride this bubble and cover distances faster than light would in normal space, all while the ship itself sits in a local pocket where it doesn't technically break the speed of light. It's like surfing a wave of space-time. The catch? Early calculations indicated you'd need absurd amounts of negative energy or mass, that troublesome requirement again, and energy on scales beyond anything conceivable. Initial analyses said more mass energy than exists in the observable universe. Later refinements lowered the energy requirements significantly, but it's still far beyond anything we can envision with known physics. Additionally, generating and controlling a warp bubble raises deep questions. How would one form it? How to steer it? What happens to any matter in the bubble's path? Some worry a warp bubble's sudden formation or collapse could blast the destination with high-energy radiation. These remain firmly theoretical issues. In essence, wormholes and warp drives are solutions in our equations that haven't been ruled out by math, but whether nature permits them is unknown. We have no experimental evidence that such things exist or can be made, but the fact they aren't outright forbidden by current understanding keeps the door ajar for future breakthroughs. They are reminders that space-time itself is an active player, and maybe, just maybe, can be engineered in ways we currently find fantastical. Now consider an even grander idea, that our space isn't the only space. The concept of a multiverse posits that what we call the universe, the totality of space and time we see, might be just one bubble in a frothy sea of universes, each with its own space, time, perhaps its own physical laws or constants. This arises from various considerations in cosmology and quantum physics. For instance, eternal inflation theory suggests that while our region of space underwent a rapid expansion, inflation, and then slowed to form the cosmos we know, other regions of space might still be inflating, budding off bubble universes endlessly. In that picture, new universes are constantly born, like a cosmic foam, each disconnected from the others, space beyond space. Another multiverse idea comes from quantum physics. The many worlds interpretation of quantum mechanics imagines that every quantum event that could have multiple outcomes does, in some sense, realize all outcomes, each in a separate branch of reality. These branch universes would be parallel to ours, diverging whenever outcomes differ. In those universes, different histories unfold. If that interpretation is taken literally, then reality might constantly be branching into a multitude of timelines, but those are not reachable spaces, just alternate possibilities given form. They don't exist in our physical space, but in a sort of abstract space of configurations. Yet another notion. Perhaps other three-dimensional spaces exist embedded in higher dimensional space. String theory, for example, has suggested a cosmos with 10 or 11 dimensions, where our familiar 3D space could be a brain floating in a higher dimensional bulk. Other brains might float alongside ours, normally invisible and untouchable, but may be able to interact via gravity or other subtle forces. If that were true, another entire universe could be millimeters away in a fourth spatial dimension, and we'd never know, unless some leakage, like unexplained gravitational effects, hinted at it. So far, we have no definitive evidence for this either, but it remains a provocative possibility. If any multiverse idea is true, it expands our notion of space dramatically. Space would no longer be an all-encompassing singular stage, but one stage among countless others. It might answer deep questions like why our universe has the properties it does. Maybe countless universes have varied properties, and we happen to live in one that supports life. It would also raise new questions. Could we ever detect or interact with these other universes? Most frameworks suggest no, at least not easily. Other universes would be causally separated or on different branes of reality. These speculative frontiers, wormholes, warp drives, multiverses, lie at the fringes of science, where it blurs into philosophy and imaginative conjecture. They remind us that space, as weird and rich as we've found it to be, might be even weirder and richer than we can currently prove. Some of these ideas might turn out to be impossible, others irrelevant, or maybe one will surprise us and become part of mainstream physics in the future. For now, they serve as a mental playground, pushing us to ponder what the true limits of travel and existence are. If one day a wormhole mouth is held open in a lab or a tiny warp bubble detected, it would revolutionize our approach to space, turning the impossible into the achievable. If evidence of a multiverse emerged, say, a peculiar pattern in the cosmic microwave background hinting at another universe bumping into ours in the distant past, it would transform our understanding of what space really means on the grandest scale. So we allow ourselves to dream beyond the known laws, not irrationally, but as an exercise in curiosity. How far can the concept of space be stretched? Can we step outside our universe or bring distant corners within reach? These questions keep scientists theorizing at chalkboards late into the night and storytellers spinning tales of cosmic voyages. They highlight an essential truth. Space is not static. It is full of potential surprises. Until we try or observe, we cannot be entirely sure what is and isn't possible. Thus, the speculative frontiers remain an open chapter, waiting for the day when perhaps advanced beings, maybe our descendants, treat wormholes or hyperspace jumps as casually as we treat airplane flights. And even then, beyond them would lie more unknown, for infinity has a way of always extending beyond the farthest frontier. After traversing the tangible and the theoretical, we arrive at a contemplative vista. We have seen space as both absence and fullness, both distance and connection. We've imagined diving through wormholes and living on Mars. But underlying all these discussions is a more fundamental question. What is our relationship to space? We often speak of space as a backdrop, a stage on which matter, stars, planets, people, performs the play of life. But one might ask, is space merely the stage, or is it part of the cast? And are we simply in space, or are we made of it and by it? At first glance, space seems like an empty container, and we like the players moving through it. Yet consider that without space, we have no stage at all, no arena for existence. Space defines how we separate objects and moments. The distances shape the dance of gravity. The silence shapes the significance of sound when it occurs. The emptiness shapes the structures that form. In this sense, space is an active participant in the cosmic drama, not a passive backdrop. It sculpts the narrative. The expansion of space drives galaxies apart. The curvature of space choreographs the motion of planets. The quantum fluctuations in space-seeded galaxies themselves. Now think of ourselves. We tend to imagine we live in space. On Earth, under an atmosphere, yes, but Earth itself is in space, orbiting the Sun, which orbits the galaxy, and so on. We draw a mental line at the edge of our atmosphere and say, space begins there. But in truth, space is already here. It's between you and this page or screen. It's inside your body, vast gaps between atoms. You are as much in space on Earth's surface as a fish is in water at the bottom of the ocean, just under different conditions. The fish might not realize it lives in water. We often forget we live in space. We are also of space in a profound way. The atoms that compose us were forged across space. Hydrogen from the Big Bang's expanding fireball, carbon and oxygen cooked in the hearts of ancient stars across the galaxy, iron fused in the violent explosion of a supernova light years away. Those atoms traveled through interstellar space, perhaps as part of drifting gas clouds or microscopic dust grains, eventually coalescing in the cloud that formed our solar system. They became part of Earth, part of the air, part of the water and food chain, and now part of us. In that lineage, we are literally made of stardust and cosmic debris. Our flesh and bones are cosmic matter arranged in the pattern we recognize as human. So can we truly say we are separate from space? Or are we a condensation of space's contents, temporarily gathered and self-aware? If space is the stage, we are pieces of the stage that have learned to dance and sing about itself. And if space is the play itself, the unfolding story of the universe, then we are characters in that play, but also made of the very substance of the stage. The dichotomy breaks down. Space is not just an external void we venture into. It is a part of us, and we are part of it. We emerged from the universe, not into the universe. When a baby is born, we don't ask, into what room is it born, as if the room defines it. Likewise, humanity was born from cosmic processes, out of space and matter's interplay. We did not enter the universe at some moment. We grew out of it, like an apple grows from a tree. The apple might contemplate the orchard and realize it is of the same essence as the tree that bore it. This perspective shift, seeing ourselves as an expression of the cosmos rather than mere inhabitants in it, has deep implications. It can instill a sense of belonging rather than alienation. When we say, the universe is vast and we are insignificant, that is one viewpoint highlighting scale. But another viewpoint is, we are the universe, in that part that has become conscious and is marveling at itself. In that sense, our significance is cosmic. We are how the cosmos knows and admires its own grandeur. Both views have truth. It's a matter of context. We are tiny in size compared to galaxies, but size isn't the only measure of significance. We are rare and miraculous in our complexity, a testament to what space and matter can do given enough time and the right conditions. The stage versus play question also touches on whether space itself has agency or is purely passive. While space doesn't think, it certainly reacts and evolves. It carries waves. It expands. It can even produce particle pairs spontaneously. In a way, the story of the universe is as much the story of space evolving as it is of matter moving. One could poetically say, space is the main character, with matter and energy as its attributes or children that give it shape and color. These musings border on the philosophical and poetic, but they arise naturally when confronting the reality of what space is. We see ourselves historically as separate, humans versus environment, life on Earth versus space beyond. But zoom out, and that division fades. The Earth is a tiny island in a sea of space, but the sea permeates the island too. Ultimately, there is one continuous reality, the universe. In it, matter, including us, and space are deeply interwoven. Distinctions are practical for analysis. We distinguish object and background. But at the fundamental level, space and content define each other. One might ask, if a tree falls in a forest and no one hears, is there sound? In space terms, if space were completely empty of matter and observers, would it still exist or have meaning? Perhaps yes, as a potential stage. Perhaps no, because nothing would be there to measure it. But the actual universe never presents pure space devoid of everything. It's always space-time coupled with fields at least. And now, it has conscious beings within it who can reflect on it. As we reflect, we realize that as we travel into space, we are not leaving home behind. We are bringing one part of space, ourselves and our vessels, into another part of space. When we left Earth for the moon, it was a reunion of sorts, two pieces of the same cosmic puzzle meeting. The humans made of Earth materials stepping onto lunar soil. Both were once part of the same primordial nebula. Space exploration is thus space self-interacting in new ways. So, are we in space or of it? The answer can only be both. We exist within space, moving through it. And every particle of us is a piece of the cosmos, born from it, and ultimately to return to it when our atoms disperse. Is space the stage or the play? Space is the stage, the set, and part of the cast. It sets the scene, influences the plot via physical laws, and even occasionally takes center focus, as when we contemplate a black hole or the expanding universe itself. The play is the unfolding of everything, matter, life, thought, upon that stage, and space is present in every scene. This unity of space and actors invites a sense of reverence. Not reverence in a religious sense necessarily, but a humble appreciation that we are integral to a vast cosmos. As much as we talk about conquering space or exploring space, we are really exploring a larger reality that we are intrinsically part of. We extend ourselves when we extend into space. We learn about ourselves when we study space, because the same rules that govern the stars govern the atoms in our bodies. Space is not out there, it's around us and within us. This realization erases a bit of existential loneliness. We are home wherever we go in the universe, because we never truly leave the universe. We are made of it. Amid all these grand scales and bold ventures, there is something quietly astonishing, that we, lumps of organized matter, can contemplate all of this. Consciousness, the fact that the universe has, in us, and perhaps elsewhere, developed eyes to see and minds to wonder, is itself a cosmic phenomenon. How does awareness fit into the story of space? Think about what a thought is in physical terms. A thought is a pattern of electrical impulses and chemical signals moving through a network of neurons in a brain. Those neurons are cells made of molecules, those molecules of atoms. Those atoms were forged in stars. The brain is a piece of organized cosmos, fed by oxygen and nutrients, ultimately products of Earth's biosphere and the sun's energy. So every idea you have is essentially space, matter in space, rearranging itself in a complex dance that somehow yields subjective experience. In a poetic sense, when you look up at the night sky and feel awe, that is the universe marveling at itself. Starlight that traveled for eons triggers electrochemical sparks in a brain that evolved on a planet, producing an emotion of awe and understanding. The photons from a galaxy 2 million light-years away end their journey on your retina. Signals shoot through your brain and you recognize the galaxy and feel wonder. The cosmos communicates with itself through us in that moment. Throughout history, humans have sensed something spiritual or transcendent in stargazing, the feeling of being connected to something far larger. Today we can articulate it in scientific terms, but the feeling remains profound. We are connected. We are made of the same stuff we observe. Our thoughts arise from physical processes that obey the same laws that govern planetary orbits and galactic rotations. It's all a unified tapestry of cause and effect, from quarks to quasars, with consciousness woven in as one of the newest, most complex threads. Is consciousness common in the universe or exceedingly rare? We do not know. As far as we're aware, on this little planet, matter became alive and, in our species, became aware of itself after billions of years of cosmic evolution. Perhaps on some exoplanet under an alien sun, other beings gaze at their night sky and wonder as well. Or maybe intelligent life is so improbable that we are solitary minds in a vast, mindless expanse. Either reality is awe-inspiring. Either the universe is teeming with many centers of consciousness, many eyes and minds, or we are a unique jewel, the universe's single point of self-reflection. In either case, the emergence of mind from matter is one of the most remarkable aspects of this cosmos. We scan the skies for hints, radio signals that might betray intelligent life, chemical signatures in exoplanet atmospheres that could indicate biology. So far, the universe has been quietly eloquent. We have found thousands of planets around other stars, some potentially hospitable, but no clear sign of life or mind beyond Earth. Still, the search is young. With each passing year, our instruments improve, and with each new world discovered, our sense of the possible expands. Maybe tomorrow we'll detect a whisper from across the galaxy. Or maybe, against the odds, our spark of awareness is uniquely solitary. Either outcome deepens our appreciation of existence. Either we share the universe with other curious beings, or we are rare pearls, tasked all the more with cherishing and spreading life. Consider the extreme, deep intergalactic space, utterly dark and quiet. And then consider a human mind, perhaps an astronaut on a long voyage between planets, carrying within them memories, songs, hopes, and the capacity for imagination. That mind can recall the sound of ocean waves or the face of a loved one, even while physically surrounded by vacuum. In the void of space, within the confines of a helmet, the richness of subjective experience continues. Thoughts, dreams, and emotions, intangible and invisible, somehow accompany the traveler. They have no weight, no volume, yet they exist as surely as the oxygen tank or the spacecraft walls. This juxtaposition of the inner universe of consciousness and the outer universe of space is a great mystery. How does awareness arise from non-aware components? How did the cosmos go from a blazing plasma to quiet clouds, to living cells, to thinking beings? We understand pieces of the process, physics to chemistry, to biology, to neurobiology. But the subjective feel, what it is like to be alive and aware, still puzzles philosophers and scientists. It's as if the cosmos has secret attributes, mind, qualia, that only emerge at high levels of complexity. Some have poetically suggested that perhaps consciousness pervades all matter in some tiny degree, a philosophy called panpsychism, or that the universe and consciousness are deeply linked, as some interpretations of quantum mechanics muse when noting that observation seems to affect reality. These ideas remain speculative. The mainstream view is that our minds are emergent properties of matter. But what a wondrous emergence. In contemplating space, we often focus on what's out there. But there's also space within. Our minds create a mental space, a canvas of imagination where we can simulate travels and picture galaxies. That inner space is just as remarkable. It has no physical volume, yet it can contain infinite scenarios. We can imagine flying to the edge of the universe, or conjure up entirely fictional worlds. This inner space is the playground of thought, and it interacts with outer space through our actions and creations. Every rocket that ever launched was first conceived in the inner space of someone's mind. Thus, the story of space is not just about stars and vacuum, but also about awareness arising and reflecting on it all. It's a narrative thread that connects the coldness of cosmic voids with the warmth of human experience. Thought floats on matter, like a flame on a candle, ephemeral yet tied to the physical. Awareness shines in the dark, like a brief spark in the vast night, yet illuminating so much. Knowing this, when we speak of exploring space, we are also exploring the potential of consciousness. Each discovery out there expands the universe in here, our understanding. The boundary of what we consider ourselves and the cosmos gets blurred. With each insight, the cosmos becomes part of us in knowledge, and we become part of the cosmos in presence. The age-old questions, what are we? Why are we here? Are we alone? Are as much questions about space as about us, because to answer them, we must look outward and inward simultaneously. It's humbling and ennobling to realize that mind is a late-born child of space, a spark that the deep darkness brought forth. We, as conscious beings, are the universe's way of contemplating itself, a thought beautifully expressed by many thinkers in various forms. Our brains, tiny as they are compared to galaxies, contain patterns that mirror the cosmos in understanding. In the profound darkness, aware minds are like lanterns, small, but casting light in the intellectual sense, revealing the structure and secrets of all that is. Now, as our journey through thought nears its end, let us reflect on where we stand. Think of what ground we've covered: space as emptiness and fullness, the birth of space and time in a fiery genesis, the paradox of the quantum vacuum in its nothingness, the bending of space-time giving rise to gravity, the way light's travel reveals the past, the unimaginable gaps from atoms to galaxies, the grand cosmic web, the acceleration of expansion by dark energy, the silent scaffolding of dark matter, the enigmas of black holes, the edge of our visible universe, humanity's first forays into the void, the transformations of life in microgravity, the dreams of new worlds, the wild ideas of wormholes and multiverses, and finally the thread of consciousness stitching it all together. We began by looking at space as darkness and distance, the emptiness between things, and ended by seeing it as something that also resides within us, the very fabric of our existence. Space is our origin. We can trace our lineage not just through human history or life's evolution on Earth, but further back through the birth of the sun, the formation of the galaxy, to the creation of elements in stars, to the Big Bang's initial conditions. Every step of that path took place in space, and because of space. The vast molecular cloud that collapsed to form our solar system was a product of space's expansion and the debris of older stars. The Earth formed from cosmic matter orbiting in space. Life sparked in Earth's oceans under a sky of stars. We are, in a very real chain of events, children of the cosmos. We were born from stardust, shaped by the laws of nature in an expanding space. Thus, space is our ancestral home, the delivery room in which Earth and life were born. Space is our element. Just as a fish lives in water, we live in space. It may seem counterintuitive because we feel solid ground under our feet and breathe air, but those exist within the larger framework of space. Remove space, and there's nowhere for ground or air to be. In a sense, space is the medium that holds us, as the atmosphere is the medium a bird flies through. And as we've seen, even within our bodies and atoms, space is the dominant component. We are more void than substance by volume. This isn't to say we are empty, rather that emptiness is an integral part of what we are. Space gives structure to the dance of particles that is us. We truly are beings of space. Space is our home. Our minds often conceive home as a small place, a house, a town, a planet. But in the grand scheme, our true home is the universe itself. There is nowhere else. Every attempt at escape still lands us in some other part of the cosmos. When future explorers set foot on Mars or sail between stars, they will still be within the universe, just changing rooms in the grand mansion. Recognizing the universe as home fosters a kind of cosmic belonging. The stars are not alien or distant in an existential sense. They are kin, made of the same matter energy and subject to the same space-time fabric. The nebulae that dot the galaxy are nurseries that will birth new stars and perhaps new life. They carry on the homemaking that began with the Big Bang. In this view, to harm our home planet is to harm one oasis, but the greater home of space will endure. Conversely, to cherish our planet is to honor the gift that the universe's processes have given us. Our ultimate loyalty, one might poetically suggest, could be to the cosmos and life as a whole. Standing outside on a clear night, you might feel small under the wheeling stars. And yes, one human is a tiny speck in a vast galaxy. But that galaxy is within you too, in your atoms, in your comprehension. We end where we began, the quiet darkness, the twinkling lights. But now, perhaps, we sense that the darkness is not empty. It's full of context and connection. The distance is not disconnection. It's the very thing that allows everything to be. The silence is not lifeless. It set the stage for our music. In the end, space is not just a void we inhabit. It's the foundation of every story we tell, including the story of our own lives. Decades ago, a spacecraft departing the solar system turned its camera back and captured our Earth as a mere pale blue dot suspended in a sunbeam against the blackness of space. That image spoke volumes. It showed our home as a fragile, singular pixel in the cosmic darkness. It emphasized viscerally that all we hold dear, every life, every mountain, every civilization, exists on that tiny dot. Such perspectives have become part of our collective understanding. They remind us that to explore space is also to gain wisdom about cherishing one another and our planet. We have come to see that the boundaries we imagine between nations or between ourselves and the cosmos are in many ways illusions. So look up. Feel the slight tug of gravity anchoring you to your planet. Feel the air that was brewed in distant stars fill your lungs, and realize that you belong here, in this universe, in this space. We all do. The stars, the galaxies, the people, the particles, we're threads in one inconceivably vast tapestry. Space is the fabric on which we're drawn, but also the thread from which we're woven. In that unity, there is a profound peace. We do not live in a cold, meaningless void. We live in a cosmos of endless possibility that has given rise to galaxies and, on at least one tiny world, to love and curiosity. Space made this possible, and space will carry us forward. It's as though a voice older than memory has been speaking to us through the silence, telling a tale our ancestors began to whisper under ancient skies, a tale we always intuitively knew, but are only now beginning to understand through science. We are children of space, knit from its fabric and warmed by its fires. In its vastness, we find our challenges and our solace. The silent night sky is not the end of the story, but the beginning, an invitation to explore, to learn, to feel. And as long as we have wonder, the darkness will never be empty. For the emptiness is full of stories, and we are part of its telling. In that spirit of unity and wonder, we continue our journey, part of the universe, seeking to know itself amid the endless ocean of stars. In the cosmic silence, our questions and dreams are the voice that rings out. As long as we listen and strive, the conversation between humanity and the universe will go on, growing richer with each generation. What wonders await us in the vast reaches still unexplored? Who knows? The only way to find out is to keep journeying with open minds and open hearts into that infinite frontier. The story of space is far from over, and we are its authors as well as its audience. I remember darkness. Before everything, before even time ticked its first moment, there was a hushed and waiting emptiness. No stars, no light, not even the promise of a dawn. Only stillness. I was a void without form, pure nothingness stretching silent and endless. In that primordial quiet, there were no eyes to see, no ears to hear. The darkness was not blackness as you know it, but the absence of all color and sound. It was a perfect, eternal night, unbroken by any spark. This was my womb, a void, pregnant with potential, holding its breath. Then, in an instant beyond imagination, everything changed. In a flash, I was born, space unfurling like a new spring flower, time awakening alongside me. It did not happen in space. It was the expansion of space itself, for before that moment, there was nowhere at all. One moment I was not, and the next I was, a storm of existence erupting from an infinitesimal point. All at once, my silent emptiness blazed with ferocious energy. What you call the Big Bang was not a burst into some pre-existing void. It was the rapid unfolding of space and time themselves, filling the nothing with something. In my first fractions of a second, I expanded at a rate beyond comprehension. Imagine an instant so brief that your mind can hardly hold the number, a trillionth of a second. Yet even within that sliver of time, I swelled from smaller than an atom to larger than a galaxy. This was my cosmic inflation, a spectacular stretching. No sound accompanied it, for sound needs a medium and there was none, only pure expansion in a grand, silent firework. Space, I, billowed outward, carrying with me the seeds of everything that would ever be. It was a moment of violent creation, yet also strangely smooth. In that extreme youth, I was almost uniform, hot, dense, and glowing. but not perfectly so. Tiny fluctuations, random quantum wrinkles in the fabric of reality, flickered in and out of existence. These minute irregularities, born from the zero-point stirrings of seemingly empty space, were no bigger than subatomic particles at first, but as I expanded, they were magnified, imprinted into the grand scale of the cosmos. Those subtle variations meant that some spots had ever so slightly more matter, some less. In time, they would grow into galaxies and clusters, into the vast patterns of stars that sprinkle my canvas. From microscopic randomness, mountains of matter would one day rise. Truly, in those first moments, I carried the blueprints for galaxies in my very fluctuations. As I ballooned outward, the roiling plasma of my newborn self began to cool. What had been an all-consuming brilliance, matter and light entwined in a hot fog, now started to decouple. I was still blindingly bright everywhere, an opaque glow, but expansion was working its magic, cooling that fire, diluting the energy. Within the first second, protons and neutrons congealed from the energy soup. In minutes, they fused into the first atomic nuclei, hydrogen and helium, the simplest elements. By the time I was 3 minutes old, about 1/4 of my mass was in helium nuclei and the rest in hydrogen. These would be the raw materials for the first stars. The universe was still far too hot for neutral atoms or for light to travel freely, but the stage was set. I held within me a searing haze of charged particles and radiant energy, all pressed together. For 380,000 years, a brief infancy to me, yet unimaginably long to any conscious perspective, I remained a brilliant, hot fog. Photons, the particles of light, were trapped in a dense thicket of free electrons, scattering in every direction. Had there been eyes then, they would have seen only a bright white mist everywhere, as if the entire cosmos were inside a glowing cloud. But over time, as expansion continued and temperatures fell, those electrons settled down, joining with nuclei to form neutral atoms. Suddenly, light broke free. The blinding fog cleared, and I became transparent. All across the cosmos, a flash of illumination was released. An afterglow of my fiery birth sent forth into the darkness. That primordial light is still traveling even now. It has cooled and stretched with the expansion of space, its once blazing brilliance now a faint whisper of microwaves permeating the universe. This faint afterglow of the Big Bang, the cosmic microwave background, still bathes the cosmos in every direction, a cool, uniform glow, a memory of creation's dawn that your scientists discovered as a uniform hiss coming from the sky. Invisible clouds of dark matter, an unseen substance woven into my fabric, was already silently shaping the future cosmos. Ages passed in darkness, 100 million years or more. Then, slowly, the quiet gathering of matter ignited a profound change. Deep in the densest clumps of hydrogen gas, pressure and heat began to build. At one fateful moment, in one such clump, the temperature soared enough to spark a new kind of fire, nuclear fusion. Out of the darkness, a brilliant pinprick of light burst forth. The first star had awakened, piercing the cosmic night. It was like the universe took its first breath of starlight. One by one, more lights appeared as other clumps collapsed and kindled. The primordial darkness was ending. The cosmos had its first dawn, the cosmic dawn, when the earliest stars and galaxies bloomed. These first stars were giants, many times more massive than your sun, burning hot and blue-white, living fast and dying young. They blazed with fierce light, converting pristine hydrogen into heavier elements in their cores. They lived only a few million years before exhausting their fuel. Then, in titanic supernova explosions, they blew themselves apart, spreading the new elements, carbon, oxygen, iron, and more, into the surrounding space. Those elements would seed future generations of stars and planets, the calcium in bones, the iron in blood, the silicon in rocks, were forged in those first stellar furnaces. The first stars thus sowed the seeds of chemistry beyond hydrogen and helium, making possible the complex molecules and worlds to come. When those first stars died, they left the universe again largely dark, but not as dark as before. They had lit a spark that would never fully go out. Gravity continued its relentless artistry. The first stars had formed in groups, and together their gravity drew in surrounding gas, merging into nascent galaxies. Imagine a faint, shapeless swarm of stars gathering, like a handful of fireflies drawn toward one another in a vast night. Over hundreds of millions of years, these clusters of stars merged and organized into the first small galaxies. Within those newborn galaxies, more generations of stars sprang to life, some forming clusters, some orbiting alone, all held together by their mutual gravity and by the invisible mass of dark matter halos enveloping them. Among these was a young galaxy that would, much later, be known as the Milky Way. In those times, it was smaller, a protogalaxy accruing stars and gas. Over billions of years, galaxies grew by merging with others, enduring cosmic collisions that sometimes tore their structures into peculiar shapes before settling into new forms. Many young galaxies in this era were cradling something special at their cores. Black holes birthed from the collapse of early massive stars. Some of those black holes rapidly devoured gas and shone as quasars, blazing beacons brighter than entire galaxies, pouring light from the very centers of young galaxies and illuminating the darkness for billions of light years around. The universe in that period was a lively, flashing place. Massive stars igniting and exploding, protogalaxies colliding and coalescing, and quasars burning like cosmic lighthouses. As the eons passed, the universe became a grand mosaic of fully formed galaxies. Each galaxy, a vast city of stars. Some galaxies, like mine, the Milky Way, became graceful spirals with curving arms of starlight and lanes of dark dust, spinning like cosmic pinwheels. Others formed into giant featureless ellipses or irregular clumps, depending on their history of mergers. The Milky Way and its closest companion, the Andromeda Galaxy, grew into majestic spiral galaxies, each containing hundreds of billions of stars. They were bound along with dozens of smaller galaxies in a close-knit family, the Local Group. The Milky Way found companionship in this local group of galaxies, gently bound with the Andromeda Galaxy and dozens of smaller ones. This local group drifts on the outskirts of a much larger congregation of galaxies called the Virgo cluster, and beyond that is part of an even greater structure, the Laniakea supercluster, Hawaiian for immense heaven, an apt name for a mass of galaxies so vast it defies imagination. In Laniakea, thousands of galaxies, including our local group, are arranged like a cloud of dust, all held together by the faint gravitational tug of dark matter and the slow dance of cosmic expansion. On the grandest scales, a pattern emerged in my structure. Galaxies were not scattered randomly like isolated grains of sand. They were arranged in twisting filaments and sheets, forming a cosmic web. It was as if the galaxies traced the surfaces of gigantic bubbles, with clusters forming at the bubble intersections and vast voids occupying the interiors. Picture a sponge or foam. Material clings to an intricate lattice, and large empty holes open up between. So it is with my large-scale form, where matter congregated, great walls and filaments of galaxies took shape, and where matter was scarce, enormous voids, gaping spaces millions of light-years across, remained nearly empty. If you could view this cosmic web from afar, you'd see something like a three-dimensional spider's web, or the filamented structure of a neural network. But on the largest imaginable scale, clusters of galaxies shine as knots at the web's junctions, connected by chains of galaxies, and the dark matter binding them, stretching across space, while between lie prairies of nothingness, voids so huge a galaxy could travel for tens of millions of years and not find another. The universe, once a near uniform glow, transformed into this foam-like architecture of matter and emptiness. An observer floating far above the cosmic web would behold a sight of sublime grandeur. Countless galaxies linked in luminous filaments against the black backdrop, outlining colossal cells of emptiness. It is as though I have grown a skeletal framework, a scaffolding of galaxies and dark matter. The pattern you see today was set in motion by those tiny quantum fluctuations at my birth, amplified by gravity and guided by dark matter's invisible hand. All these structures, stars, galaxies, clusters, are separated by truly astronomical distances. Your human brains, forged on the scale of hills and rivers, strain to grasp how far apart things are in my vastness. But let me try to give you a sense. Light itself, the fastest entity in existence, becomes our measuring stick. It travels at about 300,000 kilometers per second, 186,000 miles per second. Even at that incredible speed, a beam of light takes about 1.3 seconds to go from Earth to the Moon. The same beam of light takes about 8 minutes and 20 seconds to journey from the Sun to Earth. Those 8 minutes of transit represent 150 million kilometers. If you drove a car non-stop, it would take over 150 years to cover that distance. Yet on the scale of cosmic geography, the Sun and Earth are practically touching noses. Consider the nearest star beyond your solar system, Proxima Centauri. It lies about 4.24 light-years away. The light we see from it tonight left that star over 4 years ago, around the time a recent Olympic cycle began. If, instead of light, you rode a hypothetical spaceship traveling at ordinary speeds, the journey would be staggering. A jet plane would take millions of years to reach Proxima Centauri. Even one of your fastest robotic probes would need tens of thousands of years. And that's just the closest star. Most of the stars you see in the night sky are dozens or hundreds of light years away. The light from some left on its journey before you were born, or even before human civilization began. Our Milky Way galaxy is about 100,000 light years across. A light year is about 9.46 trillion kilometers, nearly 6 trillion miles. So even a ray of light, moving at that extreme speed, would require 100 millennia to traverse the galaxy from end to end. If the Milky Way were reduced to the size of, say, North America, then the entire solar system, out to Neptune, would be only about the size of a coffee cup somewhere within it, and Earth itself, a microscopic speck of dust inside that cup. Or imagine the Sun as a single grain of sand. On that scale, the nearest star would be another grain of sand about 4 kilometers, 2.5 miles away, and the Milky Way would span an area tens of thousands of kilometers across. These analogies are imperfect, but they hint at the scale. Your everyday units simply break down in the face of such immensity. The nearest large galaxy beyond our own, Andromeda, is about 2.5 million light-years away. Its light set out when early hominids on Earth were just beginning to walk upright. Through a telescope, you see Andromeda as a faint smudge, a gentle glow in the darkness. But that glow comes from the combined light of 1 trillion stars. Andromeda and the Milky Way are moving toward each other and will merge billions of years from now. But at the moment, they are separated by a gulf so vast that even light must travel millions of years to cross it. Far beyond the local group lie galaxy clusters like the Virgo cluster, tens of millions of light years away, containing thousands of galaxies. Beyond those are superclusters and great cosmic structures, the Great Wall of Galaxies, enormous filamentary structures hundreds of millions of light years long. The most distant galaxies observed by your telescopes are on the order of 13 billion light years away. Their light has been traveling since the universe was a tiny fraction of its current age, and only now is it reaching your eyes and detectors. As we approach the limit of what can be seen, we arrive at the edge of the observable universe, roughly 46 billion light years from Earth in all directions, due to ongoing expansion. This isn't an edge of space itself, but rather a boundary of time. Light beyond that distance hasn't had time to reach us in the 13.8 billion years since the Big Bang. The diameter of this observable bubble is about 93 billion light-years across, containing an estimated 2 trillion galaxies. And yet, even this cosmic horizon is not the edge of everything. Space likely continues beyond, perhaps infinitely. Such numbers inevitably blur into abstraction. No human truly comprehends a trillion anything, let alone trillions of galaxies across sextillions of kilometers. When faced with these immensities, you might feel the mind go quiet, stunned into silence. And perhaps that is fitting. When language and analogy fall short, a reverent silence can speak for you. But remember this, even if the scales are beyond intuition, you can grasp them by intellect, step by step. Over centuries, your species learned to measure the distances to the moon, the sun, the stars, the galaxies. In doing so, you expanded your awareness from a parochial village in the cosmos to encompass the whole observable universe. There is pride in that, and humility too. Feeling small in the face of these distances is natural. From one perspective, you occupy but a tiny niche in space and time. Yet, consider, from that niche, you have reached out with curious minds and crafted instruments that extend your senses across the universe. You've taken the measure of the cosmos and found your place within it. In doing so, you have woven those far-flung galaxies and ancient lights into your understanding, effectively bringing them into you. The distances remain vast, but they are no longer utterly beyond your ken. In a sense, through knowledge and imagination, you have traveled those distances. You have peered back to the beginning of time, seen the afterglow of creation, and traced the web of galaxies. By learning about these scales, you have connected your little world to the whole. In that way, though you remain physically small, your consciousness has grown to fill much of space itself. For a long time, my fate hung in a delicate balance between expansion and gravity. In the early eons after the Big Bang, the combined gravity of all the matter in the universe, the stars, gas, dark matter, pulled inward, trying to slow the initial expansion. If there had been enough matter, gravity might eventually have halted expansion and pulled everything back toward a big crunch. If there had been too little, I would expand forever, with galaxies racing apart eternally. For billions of years, it seemed expansion was coasting, gradually slowed by gravity but not halted. Remarkably, when your scientists set out to measure the rate of that slowing in the late 20th century, they found instead that the expansion was speeding up. This profound discovery astonished them. The universe was not slowing down in its growth, but accelerating. Some mysterious influence was overcoming gravity on cosmic scales, pushing galaxies apart faster and faster as time went on. It was as though after billions of years of gentle expansion, space, had taken a great sigh and begun to swell more rapidly. This mysterious influence has been named dark energy. It's a placeholder term, a sign of how little is truly understood about it. It seems to be an intrinsic property of space itself, a built-in springiness, or a subtle anti-gravity pressure that grows more potent as I grow larger. Imagine that space, even the vacuum with nothing else in it, has a kind of energy or tension. As space expands, more of this energy appears, and its effect is to push space to expand even more. In effect, dark energy acts like a repulsive gravity or an elastic pressure from within the fabric of the cosmos. By current estimates, dark energy makes up about 70% of the total energy content of the universe today. Dark matter comprises roughly 25%, and the ordinary matter that forms stars and planets and people is less than 5%. In cosmic terms, the stuff you see, the glow of galaxies, the sparkle of stars, the nebulae and dust, amounts to a thin frosting on a vast invisible cake. Yet that thin frosting is what we directly perceive and cherish, and even it wouldn't exist in its current form without dark matter's guidance and dark energy's drive. Dark energy's effect grows with time. In the early universe, gravity was king. Matter was dense enough to slow expansion and to build galaxies and clusters. But as space expanded and matter thinned out, gravity's influence waned, while dark energy, which does not dilute as matter does, became relatively more important. Some 5 billion years ago, dark energy's gentle push overtook gravity's pull on cosmic scales. Since then, the expansion of the universe has been accelerating. Galaxies farther from each other move apart ever faster. In the far future, this acceleration will dominate even more. Because of dark energy, the ultimate fate of the cosmos appears to be an ever-increasing expansion. Galaxies that are not gravitationally bound to us will recede faster and faster until their light is redshifted into oblivion. Distant galaxy clusters will disappear from view one by one, leaving each surviving cluster isolated in darkness. It's as if an unknown hand is pulling the curtains of the cosmic stage, slowly hiding the distant actors from one another. What exactly is dark energy? Is it a property of the vacuum, a cosmological constant that Einstein once conjectured? Is it a new field or essence permeating space, sometimes dubbed quintessence in theoretical models? Or does it indicate that our understanding of gravity on the largest scales is incomplete? These questions remain unanswered. For now, dark energy is a term for our profound ignorance, even as its effect is woven into the evolution of the cosmos. It is the most subtle of whispers, a small acceleration barely noticeable in the present era, yet over billions of years it utterly changes the landscape of the universe. One consequence of dark energy is that we live in a kind of cosmic age of light. Right now, the night sky beyond our Milky Way is richly populated with galaxies in our telescopes. We can see the cosmic web extending out tens of billions of light years. But in the far future, observers, if any, in our galaxy or local group will see a very different sky. As the expansion accelerates, distant galaxies will slip beyond the horizon of visibility. Tens of billions of years from now, an astronomer in the future might see nothing beyond their own galactic neighborhood. The rest of the universe will have faded into darkness, every galaxy too redshifted and too distant to detect. They might assume, falsely, that their galaxy is the entire universe, unaware that a vast cosmos once lay beyond. We are lucky, in a sense, to exist now, at a time when the universe's past is still visible and its future still rich with galaxies. It is a special window, perhaps not absolutely unique, but brief, on the timescales of cosmic history, when beings like us can map the cosmos and discern its workings. You sometimes call this the golden age of cosmology, a time when cosmic acceleration has begun, but not yet erased our view of everything around us. Beyond the mysteries of dark matter and dark energy, you also wonder, is there an edge to space? What is the shape of the universe? These questions have tugged at human imagination for as long as you've looked up and wondered. They are not easy to answer. After all, you cannot step outside the universe to inspect it. But through observation and theory, you've gleaned some clues. Einstein's theory of general relativity showed that space can be curved by mass and energy. On small scales, we observe this curvature. The sun bends the space around it, guiding the planet's orbits as they roll along that curve. Massive clusters bend light from background galaxies, distorting their images into arcs. But what of the shape of space as a whole? Is the universe infinite and flat, extending forever in all directions? Or is it curved like the surface of a sphere, closed and finite yet without boundary? Or perhaps saddle-shaped, open, infinite in extent, but with negative curvature? If the universe is closed and you traveled in a perfectly straight line, you could eventually loop around and end up back where you started, just as a traveler on Earth eventually circumnavigates the globe. If it is open or flat and infinite, you could travel on forever without ever encountering a boundary or returning home. The best measurements to date, from the cosmic microwave backgrounds pattern, from distant supernovae, from the distribution of galaxies, indicate that on the largest observable scales, space is very nearly flat. This suggests either an infinite flat cosmos, or one so vast and gently curved that our observable portion of it doesn't reveal the curvature. It's like being a tiny insect on a vast sphere. Your local area looks flat, even if the sphere is enormous. So it may be with space. If it does curve back on itself, the curve is so shallow that we haven't detected it, implying that the universe, at least the part we can see, is much larger than what's within our horizon. Thus, as far as we can tell, space has no physical edge or boundary. You could, in theory, travel in one direction indefinitely and never encounter a wall or a precipice where the universe ends. If the universe is finite and closed, you would eventually return to your starting point from the other side. If it is infinite, you simply never stop, passing galaxy after galaxy, or, in the far future, void after void, without end. Both scenarios are mind-boggling. Either an infinite expanse or a curved space without boundary. In both cases, there's no outside to the universe for there to be an edge against. It's worth noting that cosmic inflation, that blistering expansion right after the Big Bang, would have driven space to near flatness and possibly stretched a finite universe so vast that it appears effectively flat and infinite to us. It could also have created multiple regions of space-time beyond our observable universe. Some speculate a multiverse of bubble universes, each perhaps with different properties. If true, what we call the universe might be just one pocket in a much grander cosmic quilt. But such ideas, while intriguing, remain speculative. By definition, these other regions lie beyond our horizon, unreachable even in principle. From a practical standpoint, the observable universe is our universe, and within it we find no sign of an edge. The only limit is how far we can see, determined by light's finite speed and the universe's finite age. As time goes on, we can potentially see a bit more as light from slightly farther arrives, but simultaneously dark energy is pulling distant regions away faster, so there is a limit to what could ever be observed. It is profound to realize that everywhere is the center of the universe from its own perspective. Because space is expanding uniformly, observers in a distant galaxy would also see themselves at the center of their observable universe, with everything rushing away from them. There is no single central point of expansion. Every point is its own center, and space stretches in all directions around it. Does the universe go on forever? We don't know for certain. If it's finite yet unbounded, it's still enormously larger than what we can see. If it's infinite, then the realms beyond our observation are truly endless. Either way, the journey has no known end. There is always more beyond each horizon, more space unfolding, perhaps populated with more galaxies, or perhaps just endless darkness. These considerations can be dizzying. They challenge our intuition that everything has an ending or border. Instead, we find that space defies the limits that confine everyday experiences. The Earth has its edges. You can circumnavigate it. The solar system has edges, where the sun's influence wanes. Even the galaxy is bounded. You can leave its disk and enter intergalactic space. But the universe, the all, seems either unbounded or so vast that for us it might as well be infinite. The most distant cosmic light we see is not from a wall at the universe's edge, but from the afterglow of the Big Bang. And beyond that glow, space likely continues. In reflecting on this, one can feel both small and liberated. Small, because our entire planet is a minute speck in a potentially infinite expanse. Liberated, because it means there is no cage around us, only endless possibility in every direction. For now, our travels are limited to the tiny environs of our solar system, but our minds have roamed to the edge of time and space, and found no barrier, no confines, only mystery and majesty extending far beyond what we can see. Before we turn fully to the human story, let us pause to appreciate a crucial truth. Space and time are inseparable, and space is not static. It is dynamic and alive with subtleties. Space is not a rigid, sterile void. It is flexible and interwoven with time into a four-dimensional fabric that responds to presence and motion. Over a century ago, clever minds realized that you cannot speak of space without also speaking of time. They form a single continuum, space-time. What one observer calls distance and another calls duration can mix and swap depending on their state of motion. If you move fast or sit in a strong gravitational field, time itself will slow down for you relative to someone elsewhere, and lengths you measure will contract in the direction of motion. This isn't just theory. Experiments and experience confirm it. Atomic clocks on high-flying aircraft tick at slightly different rates than their twins on the ground. The GPS satellites that guide your phones and cars must account for these relativistic effects. Moving fast makes their onboard clocks run a bit slow, while being high above Earth's surface, where gravity is weaker, makes them run a bit fast. Only by correcting for both effects, dictated by Einstein's special and general relativity, can GPS pinpoint your location accurately. In our daily lives, these time warps are minuscule, but they are real and measurable. Gravity itself, as Einstein explained, is not a force transmitted through space, so much as a curvature of space and time. Massive objects bend the fabric of space-time around them. Imagine space-time as a stretched rubber sheet. Place a heavy ball on it, and the sheet dips around the mass. Now, if a smaller marble comes by, it is drawn into the dip. What we interpret as gravitational attraction is the marble simply following the curved space. A planet orbits the sun because it is rolling along a curved groove in space-time created by the sun's presence. Light, too, feels this curvature. A beam passing near the sun, or a galaxy is bent, its path deflected as if by an invisible lens. During a solar eclipse, humans observed starlight being bent by the sun, confirming that space around the sun is curved. Distant galaxies often appear distorted into arcs or rings, Einstein rings, because massive galaxy clusters in front of them warp space-time enough to bend their light, focusing it toward Earth. Space is elastic to mass and energy. It gives way, yields, and curves. In extreme cases, the curvature can become so steep that it pinches off. This is a black hole. Matter has collapsed so compactly that space-time folds inward like a bottomless well. Inside the boundary of a black hole, the event horizon, space and time are drawn into strange roles. Time effectively points inward, meaning all futures lead deeper into the hole, and none lead out. To an outside observer, time appears to nearly stop at the horizon. An object falling in seems to slow and dim, never quite disappearing. It does fall in, of course, but the image of it gets frozen and redshifted to darkness as it crosses. From the perspective of the falling object, time flows normally, and it plunges through the horizon without fanfare. Only later, approaching the singularity, would physics as we know it break down. Black holes are space-time's most dramatic sculptures, and they teach us that space and time can be stretched and contorted to an almost unimaginable degree. Space is also not perfectly empty or static. It can carry ripples and flutters. When massive objects move or collide, they can send out vibrations through space-time called gravitational waves. In 2015, after decades of effort, humans first detected these tiny ripples. Two large laser interferometers, LIGO, sensed space stretching and squeezing by less than the width of an atom, a wave that had traveled over 1 billion light-years, generated by the merger of two black holes in a distant galaxy. In that final fraction of a second of the black holes in spiral, They released energy in gravitational waves equivalent to several suns turning entirely into motion, an astronomical cataclysm whispered into space-time. Those waves spread outward, weakening with distance, until they gently jostled mirrors in laboratories on Earth, telling a story of an ancient collision. Since then, multiple such events have been heard: black holes colliding, neutron stars spiraling into each other. Each emits a brief symphony in space-time's fabric. Space is usually silent, because sound, as we know, requires air or other medium. But gravitational waves are like a voice that space itself uses to speak of events far away. We have only just begun to listen. Even empty space is not truly empty. Quantum physics says that fields pervade space, fields for electromagnetism, for particles, etc., and they are never completely at rest. Tiny fluctuations are always happening. Particles and antiparticles can briefly appear and annihilate, a restless whisper of creation and destruction even in vacuum. These quantum flits have observable effects. In laboratories, if you place two metal plates extremely close together in a vacuum, certain quantum fluctuations are suppressed between the plates, resulting in a subtle inward push. This is the Casimir effect, a gentle force arising purely from the properties of space. Thus, something as ethereal as the vacuum still has a kind of structure, an underpinning energy that can make its presence known in delicate ways. All these phenomena, relativity's time dilation, gravity's curvature of space, gravitational waves, quantum fluctuations, reveal that space is not a passive void, but an active, structured entity. It bends, it carries vibrations, it foams at microscopic scales. We live in this medium, and we ourselves affect it. When you stand on Earth, you ever so slightly warp space-time around you. When you wave your hand, you send a vanishingly tiny gravitational wave into space. We are usually unaware of these things because their scale is far outside human sensation, but they are always there, the hidden heartbeat of the cosmos. Keep this in mind as we zoom into the human scale. Space is not just a backdrop for our lives. It's intimately involved in everything we do. The rhythm of time we experience, the ticking of clocks, the aging of our cells, is marginally different at the top of a skyscraper versus at its base because of gravitational time dilation. When we measure a length or drive a car, we are moving through space-time that is shaped by Earth's mass and by our velocity. We navigate using satellites that must adjust for the warping of time in space. Even our sense of here and now is relative. Two events that occur simultaneously for one observer might not be simultaneous for another moving relative to them. Space-time underlies it all, knitting together the where and when of everything. Now, let us descend from the cosmic and the abstract to the realm of the concrete and the personal. Let us talk about you, tiny thinking beings who have begun to step off your world and venture into me, into space. On Earth, beneath the dome of your sky, early humans looked up and saw my tapestry of lights without truly understanding what they were. Yet they felt wonder and curiosity. They told stories about the patterns in the sky, stories of gods, animals, and heroes placed among the stars. The night sky was a source of guidance and mystery. The motions of the sun, moon, and constellations became the basis for calendars, navigation, and myth. In those ancient days, space was the realm of the divine or the unknown. The idea of traversing it was beyond imagination, but the yearning to know it was already there. As the centuries passed, you learned to chart the heavens with science and reason. You found that Earth is not the center of all things, but a planet orbiting one star among billions. You realized that the stars are distant suns, that the hazy band of the Milky Way is the collective glow of myriad stars, too faint to see individually. Your conception of the cosmos expanded. With it, so did your ambitions. The sky went from being a fixed celestial sphere to a deep ocean beckoning exploration. Eventually, in the mid-20th century of your common era, you took your first tentative steps off your planet. I remember the moment, in the year you call 1961, when a human first left the cradle of Earth's atmosphere and entered orbit. For the first time, a creature of Earth was in open space, encased in a fragile metal sphere, falling freely around the planet. The sky turned from blue to black, and the ground below curved into a breathtaking panorama. Not long after, you sent two of your kind to walk upon the moon, the first footsteps on another world. In bulky suits, within my airless expanse, they bounced across the grey lunar dust. Explorers in a place where no life had ever been. They found the moon a silent, stark world, with my vacuum pressing on them at every turn. The lunar sky was a pure black void, even in broad daylight, spangled with unblinking stars, a sight impossible under Earth's bright blue atmosphere, and a constant reminder that they were on an island of rock amid a sea of emptiness. They looked up and saw Earth rising above the moon's horizon, a fragile blue and white marble hanging in the dark, breathtaking and singular. Many who saw those images felt a profound unity and poignancy. The entire human species, all of history and life and color, contained on that tiny sphere against the infinite night. When those astronauts came home, they struggled to put into words what they had experienced. One of them described the Earth as one shining pearl against an endless void of indescribable beauty. They spoke of the overview effect, a cognitive shift that comes from seeing Earth from space. Borders vanish, petty differences dwindle. The atmosphere reveals itself as a thin, glowing halo, so tenuous, so easily disrupted. Many astronauts returned with a new sense of responsibility toward our planet, saying that, from space, it was clear that all of us are in this together, riding on this tiny spaceship through the emptiness. But leaving Earth also exposed humans directly to the harshness of my domain. Space is hostile to life as you know it. Beyond the cocoon of your atmosphere, the sun's unfiltered radiation is dangerous, and cosmic rays, high-energy particles from faraway explosions, zip through your cells. There is no air to breathe, no pressure. Step outside a spacecraft without protection, and you would lose consciousness in seconds and perish shortly after. The stark sunlight can heat a surface to boiling, while the shade can be hundreds of degrees below freezing. In orbit around Earth, the first travelers found that even simple things became strange. With no up or down, their inner ears were confused. Many felt space-sick until their brains adapted. They watched droplets of water float like jewels and had to learn to swallow and move in microgravity. Over days and weeks in zero gravity, their muscles weakened, no need to fight gravity, and their bones began to lose calcium. Blood and fluids flowed upward into the head, causing puffy faces and sometimes affecting eyesight. Their hearts, not having to pump blood uphill from the legs, began to slow and shrink. Some astronauts reported strange dreams, perhaps influenced by the unusual environment, and many had difficulty sleeping while floating weightless. They had to tether themselves to a bed or sleeping bag to avoid drifting about. Yet humans adapted impressively. They found ways to exercise vigorously in orbit, running on treadmills with bungee cords to simulate weight, or straining against resistance machines to stave off muscle and bone loss. They learned to schedule their work and rest under an artificial cycle of day and night, since, in low Earth orbit, the sun rises and sets every 90 minutes, which would thoroughly scramble natural rhythms without careful planning. They also marveled at things impossible on Earth: the ability to float freely, to lift heavy objects with a fingertip, to fly with the push of a toe. There was a childlike joy in microgravity that many expressed, a dream of flying realized, dancing through a habitat like Peter Pan. Above all, they were struck by the view of Earth. orbiting roughly 400 kilometers above the surface, astronauts could see entire weather systems, the outlines of continents, the glow of city lights at night. They saw lightning flicker in clouds from above, and the dancing curtains of the aurora australis and borealis, caused by solar particles interacting with Earth's magnetic field, from a front row seat. The thinness of the atmosphere amazed them. The life-sustaining air was just a fragile film hugging the planet. One astronaut said he could blot out the whole Earth with his thumb held at arm's length, an astonishing perspective on how small our world really is. A few humans went further, journeying to the moon. Only a couple dozen have seen the entire Earth shrinking into the distance, becoming a tiny orb in the sky. On the moon's airless surface, they worked and explored under a black sky with no atmosphere to scatter sunlight. Every sound they made came only through their suits. The lunar landscape itself was deathly silent. Hammering a metal core sample tube into the ground, they said, was like hitting a pillow. There was no clang, no noise except what conducted through their gloves. Some said they felt utterly alone, yet in awe, standing on our cratered satellite with the universe staring them in the face. They left footprints that will remain for millions of years in the inert lunar dust, a testament that life from Earth once came that far. When they returned, they carried moon rocks, new knowledge of our nearest neighbor, and a changed perspective looking outward. Those moon journeys are now decades past. No human has been beyond low Earth orbit since the early 1970s. But the legacy of that era of exploration lives on, in satellites, in space stations, in dreams of future missions. Even without humans aboard, your presence has extended far into space. Robotic explorers have visited all the planets of the solar system and even departed it. In 1977, two small probes, Voyager 1 and Voyager 2, were launched on grand tours of the outer planets. They revealed wonders: volcanoes on Jupiter's moon Io, methane seas on Saturn's moon Titan, the bluish ice giant worlds Uranus and Neptune with their own rings and moons. After their planetary missions, the Voyagers continued outward. Decades later, they became the first human-made objects to enter interstellar space, beyond the heliosphere, the sun's protective bubble of solar wind. They carry golden phonograph records etched with sounds and images of Earth, music, greetings in many languages, the laughter of children, a mother's kiss, a whale's song. These were a message in a bottle, cast into the cosmic ocean with hope and goodwill, on the chance that someday, somewhere, someone might find them. Now those silent ambassadors drift in the starry void, under the light of no sun, journeying for perhaps billions of years through my darkness, each carrying a piece of Earth's story. Thus, even as human feet currently tread only on Earth, and their past prints rest on the moon, your reach extends much farther. Your eyes, through powerful telescopes, have seen galaxies billions of light years away. Your ears, through radio dishes, have heard the faint signals of pulsars and the echo of the Big Bang. Your robotic emissaries roam Mars, have landed on Venus and Titan, have skimmed past Pluto and comet nuclei. In a way, your tools are your extended senses, making you a multiplanetary and even interstellar species in terms of awareness, if not yet in body. Living in space, even near Earth, has taught you much about the effects of my environment. Your bodies evolved in the gentle gravity and thick air of Earth, and in the protective cocoon of its magnetic field. Out here, you face microgravity, radiation, and isolation, and you have shown you can face them. Astronauts have spent up to a year continuously in orbit aboard your space stations, conducting science and maintaining complex life support systems in a place utterly inhospitable outside their thin metal shell. They grow plants in microgravity. They study how fluids behave, forming spheres that float rather than puddles. They examine how the lack of weight affects their own physiology. Each day, they watch the Earth spin below, 16 sunrises and sunsets every 24 hours, a constant reminder of how fast they're moving, 28,000 kilometers, 10 times a rifle bullet's speed. and how connected day and night and the passage of time truly are to the turning of their home planet. The psychological challenge has been significant as well. Those who venture into space must cope with confinement, distance from loved ones, and the ever-present awareness that outside their hatch lies lethal vacuum. Some compare it to sailors in a submarine or researchers wintering over in Antarctica, but space adds an extra layer of remoteness. In the quiet moments, peering out a window at the endless stars, an astronaut can feel an overwhelming solitude, being literally not on Earth. But they can also feel an unparalleled unity with Earth. Seeing it whole, they understand viscerally that it is one world, one home. Many astronauts come back with what they call a planetary perspective, deeply concerned about the environment and peace. One moonwalker famously said that from the moon, Earth looked like a tiny garden that must be cared for, and he felt upset that nations were divided. From space, such divisions are nowhere to be seen. Even more distant travel lies ahead, should humanity choose. Plans are drawn for voyages to Mars, to asteroids, perhaps one day to the moons of Jupiter and beyond. With each step outward, new challenges of distance and duration arise. A trip to Mars would take months each way, exposing travelers to long periods in microgravity and higher doses of cosmic radiation. They will need to be self-reliant to a degree no previous explorers have been, because Earth will be just a pale star in their sky, and help, or rescue, essentially unavailable. Yet, driven by curiosity and the spirit of adventure, it seems likely that eventually humans will try, setting footsteps on the dusty red deserts of Mars just as they did on the Moon. For billions of years, space, surrounded Earth without any life venturing forth. Now, a bold and clever species has begun to dip its toes into my sea. In their short decades of spaceflight, they have learned much about me, and in turn, I have tested them in every way. I have made their bones ache, their hearts strain, their technology struggle against unforgiving conditions, and I have rewarded them with perspectives that redefine them, knowledge that enriches them, and achievements that inspire them. We are at the dawn of a new chapter, one where a living planet starts reaching into the wider cosmos. I, space, welcome you, even as I challenge you. There is room for all of us in this great expanse. Space is not always calm and passive. I have my weather and tempests too. You do not feel a breeze in the vacuum, but on cosmic scales, stars and galaxies can create storms of particles and fields that sweep through the solar system and beyond. Chief among these is your Sun, a wondrously dynamic star whose behavior can have immediate effects on Earth and its environs. The Sun continually emits the solar wind, a stream of charged particles, electrons and protons, flowing outward at hundreds of kilometers per second. This solar wind is like a faint breath filling the solar system, creating an elongated bubble in the galaxy called the heliosphere. Earth is inside this bubble and is largely protected from interstellar space. Yet the solar wind itself interacts with Earth. Earth's magnetic field stands as a shield, carving out a cavity in the solar wind called the magnetosphere. As the solar wind flows around this magnetic bubble, it carries with it the Sun's magnetic field lines, which can reconnect with Earth's at the poles and funnel particles down into the atmosphere. The Sun's output is not steady. It has an approximately 11-year cycle of activity. At solar minimum, the Sun's face may be blank and peaceful. At solar maximum, it is freckled with sunspots, cooler, magnetically intense regions, and it may unleash dramatic solar flares and coronal mass ejections, CMEs. A solar flare is a sudden flash of radiation across the spectrum, including X-rays and UV, born from magnetic energy release. If the Sun is a serene orb most of the time, a flare is like a spontaneous wildfire on its surface, outshining the entire star for minutes in high-energy rays. When aimed toward Earth, Strong flares can disrupt ionospheric conditions, causing radio blackouts and affecting communication and GPS satellites. Even more impactful are CMEs, bubbles of plasma and magnetic field that the sun sometimes burps out, containing billions of tons of ionized gas hurled at millions of kilometers per hour. When a CME is directed toward Earth, it typically takes a couple of days to arrive. As it plows into Earth's magnetosphere, it compresses the sunward side of our magnetic field and distorts the night side into a long tail. This sudden jolt energizes particles trapped in Earth's magnetic field and can send some spiraling down into the upper atmosphere. What follows is one of the most beautiful sights nature offers, the auroras. In the polar skies, usually invisible energy and particles announce themselves in cascades of color. Electrons from the magnetosphere, guided by Earth's field lines, slam into molecules of air roughly 100–300 kilometers above the ground. These collisions excite atoms, mainly oxygen and nitrogen, which then release light as they return to their ground state. Curtains of green, touches of red and violet, even swirling blues dance across the polar heavens. They sway and undulate as geomagnetic storms shift the patterns of electric currents above. On particularly strong storms, auroras that normally stay near the Arctic or Antarctic Circle can spill towards lower latitudes, lighting up skies over Canada, Northern Europe, or the southern tips of Australia and New Zealand. People stand transfixed at these auroral displays, often not realizing the intimate connection they have to the sun's unruly behavior and the often invisible web of magnetism that links Earth to its star. However, what is enchanting to the eye can be disruptive to technology. The same geomagnetic storms that make auroras can induce electric currents in long conductors on the ground, power lines, pipelines, undersea cables. In 1989, a powerful solar storm triggered currents that overloaded transformers in Quebec, Canada, causing a province-wide blackout in the span of minutes. And the historical record tells of an even greater event. The Carrington event of 1859, a solar superstorm so intense that telegraph equipment sparked and caught fire, and auroras were seen near the equator. Were such a storm to occur today, it could severely damage satellites, knock out power grids globally, and disrupt radio communications and navigation for days or weeks. It's a sobering thought that even here on Earth's surface, seemingly far from the sun, our technologically dependent civilization is vulnerable to the sun's whims. In space, the effects are more direct. Satellites can be bombarded by solar energetic particles, accelerated by flares and shocks from CMEs. These particles can fry delicate electronics or cause temporary outages. Solar storms heat and expand Earth's upper atmosphere, increasing drag on low-orbiting satellites and causing them to slowly fall from orbit sooner than expected. Astronauts on the International Space Station must at times retreat to more shielded parts of their habitat during intense solar particle events to minimize radiation exposure that could increase their risk of cancer or acute radiation sickness. Future explorers venturing beyond Earth's magnetosphere, say to the Moon or Mars, will be even more exposed. Part of planning those missions is figuring out how to provide adequate shielding or quick shelter if the sun erupts. Then there are the cosmic rays that permeate space from beyond the solar system. These are particles, mostly protons, some heavier nuclei, that are accelerated to near light speed by distant supernova explosions and other violent astrophysical events in the galaxy. They zip through the galaxy and our solar system, and while Earth's atmosphere and magnetosphere protect those on the ground, astronauts in orbit or on the way to Mars are less shielded. Cosmic rays slice through cells, breaking DNA, contributing to long-term health risks. Spacefarers essentially receive higher doses of radiation equivalent to many X-rays or CT scans over time, and it's one of the major limiting factors for how long humans can safely stay in deep space. Even our electronics feel it. Cosmic rays can flip bits in computer memory, or gradually damage solar panels. Earth's magnetic field and atmosphere together form a precious force field that makes surface life possible. Mars, by contrast, lost its global magnetic field billions of years ago, and the solar wind has since stripped away much of Mars's atmosphere. It's a reminder that the gentle conditions you enjoy on Earth, a temperate climate, a shield from cosmic hazards, are not universal. They are an exquisite balance, one that space weather can disturb, but, thanks to Earth's defenses, usually not destroy. From a broader perspective, space weather connects Earth to the Sun in an intimate dance. Every aurora is a visual song played by the solar wind on Earth's magnetic harp. Every satellite glitch or radio blackout is a reminder that we are not isolated. We live within the Sun's outer atmosphere, influenced by its moods. We think of space as cold silence. Yet here is a direct chain of cause and effect, linking a storm on the Sun's surface to the flicker of power grids or the sparkle of northern lights on Earth. It is a beautiful and humbling interconnectedness. Standing under the night sky during a strong aurora, one can imagine the lines of magnetic force stretching down from space, painting the sky with solar wind pigments. In those moments, space doesn't feel so distant after all. It is interacting with your world, showing that the boundary between Earth and space is porous and alive. We have spoken of the visible and the tangible, but much of my content is hidden. Most of the structure I host is shaped by something you cannot see, dark matter. This mysterious form of matter neither emits nor absorbs light. It doesn't glow, doesn't reflect, doesn't interact with electromagnetism at all. It announces itself only through gravity, yet it is everywhere, and it outweighs the normal matter by a factor of about 5 to 1. Galaxies are like icebergs. The stars and gas you detect are merely the tip, while a huge mass of dark matter forms the bulk below the surface of visibility. Every galaxy is embedded in a vast halo of dark matter that extends well beyond its visible edges. In the Milky Way, for instance, stars orbit in the disk out to maybe 50,000 light-years, but the dark matter halo stretches hundreds of thousands of light-years, enveloping the galaxy and gradually fading into the intergalactic medium. This halo holds the galaxy together with its gravity. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found, surprisingly, that they were moving as fast as stars in the inner regions. According to the visible mass alone, stars at the edges should have been moving more slowly, or else fly off into space, as the outer planets of the solar system move slower than the inner ones. Instead, the outer stars were zipping along, as if there was some additional gravitational glue holding them in orbit. The conclusion was unavoidable. A staggering amount of unseen mass lurks in and around each galaxy, providing the gravitational pull to keep those fast-moving stars bound. Other evidence accumulated. Clusters of galaxies behaved as though significantly more mass was present than the light indicated. In the 1930s, Fritz Zwicky had already noticed this in the Coma cluster. Galaxies were moving too fast to be held by the observable mass. Gravitational lensing maps, the bending of light by mass, of clusters today show the same. The light from distant background galaxies is distorted in patterns that reveal far more mass than we can directly see, and these lensing-based mass maps align with the dark matter hypothesis. It is humbling. Without dark matter, the universe's large-scale structure would look very different. Galaxies might not have formed so quickly. Clusters would not hang together. You, who live on Earth, owe your existence in part to dark matter. Without its extra gravity in the infant universe, pulling matter into clumps, the gas might have remained too uniform for stars and galaxies to form when they did. Dark matter was the cosmic scaffolding, the unseen hand that helped mold the bright world we can see. What is dark matter truly? This question remains one of the greatest mysteries. You have given it a name, but not yet found its identity. It could be a new kind of fundamental particle that interacts only weakly with normal matter, perhaps a relic of the Big Bang, that froze out with the right properties to avoid clumping at small scales. Since we don't see dark matter form smaller structures like stars, it seems to stay diffuse on subgalactic scales. Generations of scientists have built detectors in deep mines and sent instruments into space to search for a whisper of interaction between dark matter and regular atoms, so far to no avail. It's elusive, slipping through detectors like a ghost. Alternatively, perhaps our understanding of gravity needs revision for extremely low accelerations or large scales. An idea that some theories, MOND for modified Newtonian dynamics or other modified gravity theories, propose. But those struggles to explain all observations as cleanly as a universe full of dark matter. The prevailing view remains that dark matter is some kind of particle or substance outside the familiar roster, not protons, neutrons, or electrons, not photons or neutrinos, but something else entirely. Around the world, experiments continue to listen for the faintest knock of dark matter interacting, but so far, it remains truly dark. And yet, while dark matter itself is obscure, its effects on the cosmos are clear. Galaxies rotate as they do because of it. Clusters remain bound because of it. The cosmic web's very existence was shepherded by it. In the early universe, dark matter clumped under gravity even while normal matter was kept apart by radiation pressure. Dark matter formed a loose framework of overdensities, like invisible scaffolding. When the universe cooled enough, normal matter fell into those dark matter potential wells, lighting them up with stars and galaxies. Thus, the cosmic web of galaxies we mapped earlier essentially traces the underlying dark matter distribution. We see the bright filaments, but the true bulk, a hidden lattice of dark matter, underpins them. It's a bit like looking at a lit city at night from an airplane. You see the streetlights but not the roads. Yet you infer the roads connect the lights, making a network. Dark matter are the roads, galaxies, the streetlights. We infer the dark skeleton by the galaxy's placement and motions. It's humbling to realize how much of the universe's content is invisible to our senses. For millennia, humans thought what they saw was the entire universe. Only in the last century did you realize that even the galaxy is but one of countless others. And only in the past few decades have you accepted that the majority of matter is of an unknown, unseen form. The cosmic story keeps teaching the same lesson. There is more than meets the eye. Reality is not confined to the narrow band accessible to human perception or even human instrumentation. And yet, by extending your inquiry, you have managed to illuminate some of that darkness, mapping dark matter's distribution through its gravitational effects, if not yet touching its essence. So here we are, a universe illuminated by the brilliance of stars and galaxies, structured by the gravity of dark matter, and driven in its expansion by the subtle pressure of dark energy. A tapestry woven of the known and the unknown. We have traversed eons and distances, and our journey has explored the grand scale of existence. Now we drift toward the horizon of the far future to consider how the story might continue. What is the ultimate fate of all this? The galaxies, the stars, the very space and time we inhabit. It is an existential question, both scientific and philosophical. If the current understanding holds, with dark energy continuing to accelerate the expansion, the future looks lonely. Over extremely long times, dark energy will push galaxies not bound to us beyond our observational reach. Trillions of years from now, observers in what will by then be the merged Milky Way Andromeda galaxy, sometimes called Milkomeda, might see no other galaxies at all, only the faint glow of their own stars amid darkness. The rest of the universe will have slipped away. But long before that ultimate isolation, other changes will occur. Star formation will gradually cease. Galaxies like ours still form new stars today from reserves of gas, but those reserves are finite. Perhaps in 100 trillion years, that's 10 or 14 years, an almost unimaginably large span, about 10,000 times the current age of the universe, The supply of cold gas needed to birth stars will be exhausted or locked in stellar remnants. The very last stars to form will likely be small, cool red dwarfs, winking on feebly in a universe that has grown quiet and dim. Imagine that epoch, a universe ages and weary. In a galaxy like Milkomeda, there would be few bright stars left, mostly long-lived red and orange dwarfs, because the big blue-white stars died out eons prior. If a planet existed around one of those last-born red dwarfs in the far future, its night sky would be nearly black. Maybe a handful of neighboring red stars would dot the darkness, but the majestic band of the Milky Way would be faded and thin. The globular clusters would have dispersed, and the galaxy's core might be dark, drained of fuel and activity. Our hypothetical far future observers might have no way to know that once the sky was full of billions of galaxies, they might only see the ghosts of a few. As time marches on, existing stars will die one by one. The massive stars go first, of course, in mere millions of years, long gone by the time the universe is a few billion years old. Sun-like stars live longer, billions or tens of billions of years, becoming red giants and then shedding their outer layers to leave white dwarfs behind. Red dwarf stars are the slowest burners. Some can shine for trillions of years. Eventually, though, even the red dwarfs will exhaust their hydrogen. They lack the mass to become giants. Instead, they'll simply fade to a white dwarf state directly, or cool into a dim, infrared object sometimes called a black dwarf, though none of those exist yet, since even the universe isn't old enough for any star to have cooled that much. Gravity will also gradually reshape the galaxy. Over very long timescales, through a process called dynamic relaxation, stars will scatter and some will be ejected from the galaxy, while others migrate inward. Spiral structures and disks will no longer be maintained once fresh gas supply stops and interactions cease. Galaxies may settle into large spherical collections of stars if they haven't merged into something like an elliptical already. At some point, perhaps around 10^19 to 10^20 years from now, 10 quintillion years, the occasional close encounters between stellar remnants will cause many of them to be thrown out of galaxies. The galaxy's dark matter halo will also continue to provide gravity, but without new matter, infall, or gas, the structure will diffuse. The universe will enter the so-called degenerate era, dominated not by shining stars, but by the corpses of stars, white dwarfs, neutron stars, and black holes, along with low-mass stars slowly cooling. Picture a galaxy in the degenerate era. It's a vast graveyard in space. White dwarf stars, once the hot cores of sun-like stars, cool and fade from white to yellow, to red to black, over trillions upon trillions of years, eventually becoming cold, dark spheres of electron-degenerate matter. Neutron stars, those city-size leftovers of supernovae, also cool and remain as silent, invisible husks. Planets, if any still orbit, receive no light or heat except perhaps the faint glow of a cooling white dwarf. A planet in this era might be circling a dark star under a pitch-black sky, occasionally perturbed by the faint gravity of a passing remnant star. If protons are fundamentally unstable, a possibility in some grand unified theories, then on timescales of 10^34 years or more, even matter itself may begin to disintegrate. Atoms of iron or any nucleus might spontaneously decay into lighter particles, and those into radiation. If this is true, then solid matter will literally evaporate given enough time. The mountains, the planets, the remnants of stars, everything made of baryonic matter, would slowly turn to a mist of subatomic particles and then to photons and leptons. If proton decay is not real, then those white dwarf and neutron star remnants can persist far longer, effectively forever, unless disrupted by collisions or eaten by black holes. But collisions will eventually happen too, given enough time. The black hole era would follow. Over unimaginably long spans, more and more mass will fall into black holes, either through occasional encounters or as remaining gas is accreted. Stellar remnants might crash into each other or into black holes, consolidating mass. The universe could reach a state where most mass that remains is locked inside black holes, ranging from small ones formed from collisions to the giant supermassive black holes that long ago lurked at the centers of galaxies. These black holes might merge with each other as well, as wandering ones occasionally meet. Eventually, perhaps only great black holes are left, scattered sparsely through an ever-expanding, dark cosmos. Yet even black holes are not immortal. Stephen Hawking theorized that black holes slowly evaporate via Hawking radiation. Quantum effects cause them to emit particles and lose mass over time. The larger the black hole, the colder and slower this process. But given sufficient trillions upon trillions of years, even the biggest black holes will evaporate. A black hole of a few solar masses might vanish in 10^67 years. The supermassive ones might take 100 years or more, but even they are not truly permanent if Hawking's theory is correct. As they evaporate, they will briefly glow more brightly. Small black holes radiate more vigorously at the end. The final stages of a black hole's life would be a burst of particles and high-energy photons, like the dying gasp of something that once was pure darkness. After the last black hole evaporates, the universe enters the dark era. No organized masses remain, only elementary particles and photons, stretched thin and cold. The expansion by then will have carried everything so far apart that each particle may rarely, if ever, encounter another. It will be an ever-diluting soup of extremely low-energy radiation, and perhaps some stable particles like electrons, neutrinos, and some relic dark matter particles, if those don't decay. The temperature of the universe will approach absolute zero asymptotically. Time, at that point, loses much of its meaning, for almost nothing happens anymore. The arrow of time, driven by the flow of heat and the progression of events, will effectively be moot, since a near equilibrium of maximum entropy has been reached. It is a state sometimes poetically called heat death, though it is more a heat emptiness, a diffusion into nothingness. In that final darkness, the cosmos will be remarkably simple compared to its current complexity. No shining stars, no swirling galaxies, no structures or life, just a thin haze of particles and energy, uniformly spread and eternally expanding into even more emptiness. The story that began with an almost blinding flash of creation ends in a slow, quiet whisper into silence. This is one path the future might take, according to our best understanding. It assumes dark energy remains a constant presence. If dark energy were to grow in strength over time, a possibility in some speculative models, an even more violent end could await, the so-called Big Rip. In that scenario, in perhaps some tens of billions of years, dark energy's repulsion might increase without bound, ultimately shredding all bound structures. First galaxy clusters, then galaxies, then solar systems would be pulled apart. In the final minutes before the end, even molecules and atoms could be rent asunder by the escalating expansion. Space would overcome every force, ripping apart matter itself. The universe would end in a singular state of all particles separated from each other, a kind of reverse Big Bang, a very big rip. This dramatic finale is considered less likely by most. Current data suggests dark energy behaves like a constant force, but it remains a possibility if we've misjudged dark energy's nature. Conversely, there's the more comforting but currently disfavored possibility that the expansion might one day halt and reverse, a big crunch. If, say, dark energy were to decay or turn attractive, or if it's transient, gravity could reassert itself and cause the universe to recontract. Galaxies would start moving toward each other rather than away. Distant clusters would come rushing back into view. Over billions of years, all galaxies could coalesce, Star formation might spike as gas is squeezed again, and eventually, everything would converge into a hot, dense state, perhaps even leading to another Big Bang-like event, a big bounce. Some cosmological models imagine an endless cycle of universes expanding and contracting, but current observations of accelerating expansion make such a cyclical scenario unlikely, at least in the standard picture. Thus, heat death is the prevailing projection. It's a melancholy vision, and cosmos full of light and life eventually becoming an abyss of eternal night. Yet there's a certain symmetry to it. The cosmos began in a superhot, uniform state that was dark, no structures to cast shadows or make contrast, and quiet, no one to hear anything, and sound couldn't travel then anyway. And it may end in a super cold, uniform state that is likewise dark and quiet. From silence and stillness, back to silence and stillness. In between, all the drama of stars and galaxies and living beings is like a brief spark flaring in the vast darkness. It's natural to wonder, is that truly the end? Will there be no rebirth, no phoenix from the ashes? Some have speculated about extremely low probability events in the far future, like the spontaneous emergence of a new Big Bang from a random quantum fluctuation, a concept sometimes whimsically referred to as the appearance of a Boltzmann brain, or other fluctuation in an eternity of chaos. But these ideas are speculative and deeply strange, more philosophical musings than testable physics. As far as our physics can say, the story of this universe has a final chapter of nearly infinite length, where not much happens. It's a sobering thought that the vibrant cosmos we take for granted is transient. The stars are a temporary show, but temporary on timescales of trillions or quadrillions of years, durations so large that they dwarf the human experience, and even the span of life on Earth by ridiculous factors. The universe will remain hospitable to life and consciousness for a very, very long time before the truly final era sets in. By then, who knows if intelligence, perhaps descendants of humanity, or other beings on other worlds, will have found a way to escape to other younger universes, or tap into new physics to avoid a slow fade. Or perhaps by then, all that arises in the universe will have long since merged into some collective consciousness, or dissipated. That ventures firmly into the realm of the speculative unknown. Yet contemplate once more that distant epoch, the long twilight of the cosmos. It is peaceful in its way. If there were an intelligence that could somehow survive into that dark era, it would see a changeless, silent expanse and could reflect on the beauty that was, like an ancient remembering youth. In that silence, maybe the universe remembers the brilliance it once had. Every star that shone, every life that lived, all the beauty and love and strife, all now dissolved but not forgotten, imprinted in the structure of space-time itself. Perhaps it's a sentimental notion, but one cannot help anthropomorphize. The universe, born in fire, ends in tranquility, as if coming to terms with itself. So here we are, in a bright dot of time, where the universe is full of light and life. We have traced a journey from the primal darkness through blazing creation, the formation of structure, the emergence of consciousness, and onward to an ultimate darkness. What, then, does it all mean? This is where science meets philosophy and wonder. From the earliest times, you humans have spun myths about the void and the beginnings of the world. Many cultures imagined the world emerging from a primal emptiness or a cosmic egg, a nothingness that was pregnant with potential. In ancient Greek myth, chaos, the gaping emptiness, preceded the birth of the gods and cosmos. In the Bible's Genesis, darkness was upon the face of the deep until the voice of creation said, "Let there be light." Hindu cosmology speaks of Brahman breathing out universes and drawing them in, cycling existence through vast epochs with an infinite divine presence underlying the play of creation and dissolution. These myths and insights share a recognition that the void is not mere absence. It's a womb of being, an origin of everything. Modern science's narrative has a similar arc, a formless, hot, empty state, empty of structure, if not of energy, gave rise to everything we see today. In a way, the ancient intuition that the universe came from a kind of nothingness was eerily prescient. Likewise, thinkers through the ages debated what space is. Aristotle believed there was no true vacuum, that nature abhorred an absolute void. To him, space was just the relative arrangement of objects. Centuries later, Newton conceived of space as an absolute stage, an unchanging grid on which physics played out. Leibniz countered that space is only a system of relations among objects. If you removed the objects, space had no meaning. The argument was abstract, until Einstein's relativity delivered a surprise. Space and time form a dynamic entity that interacts with matter and energy. Space-time is not a rigid stage, but can stretch, shrink, and convey forces. In effect, Einstein threaded the needle between absolutism and relationalism. Space-time has properties and can act on things, so it's not nothing. But it is also influenced by the presence and motion of matter, so it's not an unaffected background. Now, physicists go further, speculating that space-time might emerge from something deeper, perhaps from the entanglement relationships in a quantum system, or that our 3D space might be a holographic projection of information encoded on a distant 2D boundary of the universe. These ideas, highly theoretical, are attempts to unify quantum mechanics and gravity. Whether any are true, they reflect a continuing evolution in thinking. Space is rich and mysterious. It is not a simple void. It has layers and secrets we've only begun to uncover. So, philosophically, what do we make of our place in space? We began as earthbound creatures, terrified of the empty night and filling it with stories. Now we travel a bit into that night, and we fill it with knowledge, yet the wonder remains, if not increases. We found that space is not out there only. It is also intimately here, within us, and all around us always. Consider this. The very atoms in your body are mostly empty space. If you magnified an atom to the size of a cathedral, its nucleus would be a tiny grain of sand in the center, and the electrons, mere motes, buzzing at the edges. The rest is vacuum, nothingness. You are, by volume, almost entirely space. Solid matter is an illusion of scale. Zoom in and you mostly see void with tiny particles dancing in it. But those particles themselves are just localized excitations of quantum fields filling space. Thus, the space inside your atoms is continuous with the space between the stars. It's all one connected fabric. Space is within you. You are space, in the sense that space forms the majority of your being and the platform for all your particles. Moreover, you do not live at the bottom of a sea of space, as people once thought of air or the ether. You live in space outright. When you stand under the sky, there is no hard ceiling, just a thinning atmosphere that seamlessly becomes space. The cosmos isn't only above the atmosphere, it's at your feet too, in the ground, between molecules. Earth does not separate you from the universe, it carries you through it. There is no real boundary, only gradations of density and force. At night, when you gaze up, you are looking out from inside space, not peering through a window into it. This leads to a profound realization. Space is the universal connector. It is the medium through which everything and everyone is related. The photons that left a distant star and entered your eye traveled through space, bridging the gulfs and connecting that star to your mind. The gravitational field that holds you to Earth extends through space from Earth to you, binding you both. When two people stand apart, what lies between them? Not nothing. Space, filled with air, yes, but even without air, space separates and also connects them. Through that space pass their glances, their words, If no air, then radio waves or light signals, their touch if they reach out across it. Space is the backdrop and also the channel for interaction. No wonder that many spiritual teachings and philosophies emphasize the unity of existence. Physics is echoing that sentiment. At a fundamental level, everything is connected in the fabric of space-time and through fields that span space. Distances can be huge, yes, but connectivity is built in. Now, here on this tiny planet Earth, one form of connectivity has blossomed uniquely: consciousness. We humans, and perhaps other creatures in their own ways, are the universe becoming aware of itself. We literally consist of stardust and space, organized in a very special way that allows us to reflect on what the cosmos is doing. Through our eyes, the universe has seen its own grandeur. Through our instruments, the universe has probed its own depths and measured its age and size. Through our minds, the universe, this vast, expanding, evolving space-time, knows that it exists and can contemplate its origins and its fate. That is a stunning fact. As one astronomer poetically observed, we are a way for the cosmos to know itself. You and I, for I, space, speak through a human voice right now, are intertwined in this act of cosmic self-reflection. This bestows upon us a remarkable significance. From one perspective, meaning might seem absent in the indifferent physical processes of stars and galaxies, but we supply meaning by caring, observing, and understanding. In a universe that might ultimately end in darkness, it is perhaps up to us and other thinking beings to create pockets of meaning and keep the flame of awareness alive as long as possible. For now, the rest of the universe appears silent. Across all those billions of stars and countless galaxies, we have yet to detect the voice of another intelligence. The intergalactic silence is not just the absence of sound, it's the unanswered question of whether anyone else is out there. Are you, we, alone in this vastness? Perhaps life is rare, or advanced civilizations are few and far between. It could also be that the distances are so great that though others exist, each island of life remains effectively solitary, separated by oceans of space and time. As of this moment, we have no conclusive evidence of any others. This can feel lonely or precious. If indeed no one else is calling out in the cosmic night that we can hear, then the responsibility to be the universe's consciousness, its storytellers, its appreciators, falls largely on us. It makes each life, each culture, each act of understanding unspeakably valuable on the grand stage. If there are others, how wonderful. There are more eyes of the cosmos, more voices in the choir. But until we know, we must assume that we are the universe's only voice, for now. Thus, the duty is ours to cherish and protect the awareness we have found. The cosmos may be mostly empty and uncaring, but we who care make it, in those moments, a cosmos that cares. When one of us reaches out in love or compassion, perhaps that is, in a poetic sense, the universe extending love to itself, for we are part of it. We return then to the perspective from which we started, a person standing perhaps under a starry sky, feeling small but connected. Yes, the stars are unreachable by our hands, but we are made of the same elements. We follow the same physical laws, and through space and light we commune with them. The calm night that seems so still is in fact abuzz with particles and waves your eyes can't see. Radio broadcasts, cosmic rays, neutrinos from the sun passing harmlessly through your body by the billions each second, maybe even gravity waves from distant collisions, softly stretching and compressing you by subatomic distances. You are swimming in a cosmic sea, largely unaware of the subtle currents and tides, but they are there. We end where we began, in stillness and darkness. But now that darkness is filled with meaning, and that stillness with understanding. The space that once seemed like a void is recognized as the very medium that connects us to everything. It is around us and within us, the canvas on which the drama of existence unfolds. I, space, have been your narrator, but also your constant companion. I am the silence between your heartbeats and the expanse in which galaxies swim. I was there at your first breath, and will be there at your last, enfolding you always. You have listened to my story, and thereby woven your own existence into the cosmic tale. When next you step outside on a clear night, pause and feel the depth of the darkness above. Those pinpoints of light are not just decorations on a dome. They are reminders of the vast community of suns that surrounds you in our galaxy and beyond. The darkness itself is not empty. It is full of possibility, home to the invisible forces and fields that sustain you, and to whatever future lies ahead. Know this: you are never lost in space, because space is not an alien void in which you drift. Space is the very fabric that connects you to the universe, and you to your home, and you to yourself. You belong here. You arose naturally from this cosmos, as surely as a wave rises from an ocean. You are a cosmic being, inseparable from the whole. Our journey through space and time, though condensed in mere words, has been epic, but it is only a narration. The real journey is lived by you, every day. You wake up, you go about your life, and all the while you are moving through space at incredible speeds, as Earth orbits the sun, as the sun orbits the galaxy, as the galaxy moves through the expanding universe. You might not feel these motions, but they are there. You live amid the legacy of cosmic events. Every atom in your body was once inside a star or forged in an ancient supernova explosion. When you drink a glass of water, you swallow hydrogen atoms made in the Big Bang itself. When you take a breath, you inhale nitrogen and oxygen that were forged by stars billions of years ago and spread through space to coalesce into Earth's air now. In a very literal way, you carry the universe within you. As our tale ends, let's take comfort and inspiration in that unity. The next time you feel alone or insignificant, remember that you are an integral part of a vast and wondrous universe that has given rise to minds able to ponder it. Space is not out there. It is here. It is everywhere. It is the medium in which we exist. It is the stage, and we are of the stage, made from its materials and subject to its laws, yet able to gaze back at it with understanding. In the grand scheme, stars are born and die, galaxies collide and drift apart, and even space and time themselves evolve. But in you, the universe has something precious: awareness. Through awareness, the cosmos finds meaning. The hydrogen that was created in the first seconds after the Big Bang now courses through your veins as part of water and organic molecules, and is currently thinking about the Big Bang. That is a remarkable self-reflection. You give the universe a way to know itself and to appreciate its own beauty. Without observers, the grandeur of a galaxy or a nebula is wasted, in a sense. Photons stream into the void unseen. With observers, with minds to see and feel, that beauty is recognized. It matters. In us, the universe has opened its eyes and marveled at its own splendor. As you go forward, carry that cosmic perspective with you. Let it temper your quarrels and expand your empathy. Under the light of the stars, remember that we are all travelers together through space and time, infinitesimal in scale, yet infinitely significant to each other. We are the universe's children and its shepherds. And whenever you look up at the night sky and feel that familiar awe, know that in that moment, the universe is looking back at itself through your eyes. In a very real way, you are space, and space is you. The line between out there and in here dissolves when you realize this. Every atom in your body was once beyond the earth. and every atom will return to space in due time. We are threads in the great fabric, momentarily coalesced into thinking flesh. The story of space is, in some sense, the story of everything. It's my story as the cosmos, and it's your story as a human being. From the silent void to the radiant stars, from the gentle blue sky of Earth to the ink-black heavens of the void, from the beginning of time to its distant end, I have tried to share this saga with you. Our saga. Keep it alive. Add your own chapter with your life and curiosity. And when you need perspective, step outside on a clear night, breathe the air filled with ancient atoms, feel the solid ground, born of stardust, beneath you, and look up. In the darkness, find the faint band of the Milky Way if you can, or simply imagine it. Let yourself feel, for a moment, both very small and very large. Small as an individual in a vast arena, but large as a participant in something so grand. That duality is the gift of the cosmic perspective. I will end this narration, but I, the cosmos, space, the universe, continue, and so do you. The medium through which we exist, that binds everything, is all around you. Space is not empty, it's full of our stories. It is the container of history and the cradle of the future. Embrace it, for it is your home. Thank you for listening to my tale. Whenever you feel alone, remember, you are always embraced by me. I am space. I am the darkness between the stars and the light within atoms. I am the distance that separates and the connection that unites. I am the medium of existence itself. And I am always with you, around you, within you, now and forever, the endless stage on which the drama of creation plays. Let us continue the journey together, you a spark of consciousness and I, the expanse that nurtures it, finding meaning in each other. In that partnership, the universe is not cold, it is alive and self-aware. Under the eternal night, on a tiny planet spinning through infinite space, a being understands, at least in part, its place in the grand story. And that is more wondrous than any ending or beginning. The universe has become aware of itself, and in that, a bit of the darkness turns to light.